will be okay, good. Our first speaker will be Carlo Maccaferri, and he will talk about closed string deformations in open string field theory. So please go ahead.
Okay, so thanks a lot. I hope you can see my screen. And okay, so this is I'm going to talk about these 3 papers and some work in progress I did with Jakub Voschmera. Okay, so now I can. Okay, I hope. So this Zoom is really, I cannot see my screen. So okay, so so this is more or less what so the motivation the motivation is try to capture the physics of open and closed strings inside a full complete setting, which is hopefully also non-perturbative, and this so in principle should be open closed string field theory and its path integral. Right, but open closed string field theory is computationally hard. Okay, so it's we don't really know some really complete form, analytic techniques, and classical solutions. But there is a limit of open closed string field theory, which is fairly tractable, and this is Witten type open string field theory deformed by the Shapiro-Thorne open closed coupling. And in fact, this is a limit in a family of interpolating open closed string field theory that Barton Zwieback discussed several years ago. So I will focus on this limit and see how far we can get. And with the idea that when problems will arise, I will always have in mind that this is a sort of limit. And therefore, I will try to solve problem by recasting them in this deformed open string theory inside a fully regular open closed string field theory. Okay, so let's start with the bosonic string. So that's the story for the bosonic string deformed with an Elwood invariant, the Shapiro-Thorne vertex, also called Elwood invariant. This is the usual form of.
Sorry, Carlo, are we supposed to see more than the title of your slide?
You're supposed to see the formulas.
I don't see any formulas. Is that just me or?
No, we're not seeing anything, just the title.
Oh, that's very unfortunate because I can see them. That's
okay, that's weird.
That's very weird. I don't know what to do now because
maybe stop the screen sharing and try again.
Wait, it says me.
I think you have to share the desktop, not the PDF file.
Okay, yeah, okay, so let's see. So now so share screen, share desktop. Okay, and so now do you see the formulas now?
It's black or
not yet.
So there are no formulas coming out and there is nothing. So now it says to me that I'm sharing the screen. So it's really formula. This is Witten string field theory deformed by this tadpole here, which is controlled by this string field E. Now this thing is gauge invariant if E is killed by Q, the open string Q, and if it commutes in the sense of the star product with psi. And this realized if this thing is a midpoint insertion of a 0,0 primary on the identity string field. And so now, okay, the gauge structure is the same. It didn't change, but the vacuum structure is changed because now we have a source in the equation of motion, and therefore psi equal naught is no more a solution, and every classical solution is no more a solution and has to be shifted in order to become a solution. Now, the fact is that it is not guaranteed that for generic E, a solution can be shifted. And this thing, in fact, is controlled by the bulk boundary OP and by obstructions. So you write the vacuum shift solution in power series expansion in the closed string deformation, and the first equation you find is precisely this one. Now you see this equation is looks strange because it tells you immediately that if you want to solve this equation for psi1, E must be BRST exact. But you would not expect it to be BRST exact because this it is a physical closed string state, so you don't want it to be trivial. But in fact, this is a statement in the open string Hilbert space, and in fact, it is a statement about the OPE between the two chiral and anti-chiral components that compose the clustering. In fact, so what is called the bulk boundary OP. So what happens is that if these two chiral fields, chiral and anti-chiral that compose the clustering field, generate a weight one field in their OP, then you have problems, because then in this state, also thanks to C, you can create CDAL CV1. And if you create CDAL CV1, then you have a Gauss number 2 element of the open string homology, and then you are abstracted. So a related boundary conformal theory analysis of this phenomena was done by Fredenhagen, Gabriel, and Keller some years ago. So this is supposed to be the open string field theory side of the story. So let's try to look at this vacuum shift solution more closely. How can we build it? We can build it just using the open string propagator, which is this common form in single gauge. Here I just have added this P0, which is fundamental, which makes through this Hodge-Kodaira decomposition, and P0 is the projector in the kernel of L0. So with this object, we can write down, as usual, all the elements of all the higher component of the solution. And in fact, we can even repackage everything in a coalgebra language in this form. Okay, so, but that's not the end of the story. Okay, so here we have just solved the equation of motion outside of the kernel of L0. So we have to be sure that inside the kernel of L0, the equation of motion are solved. And this is provided by the vanishing of these quantities. Now, what are these quantities? So P0 projects into the kernel of L0, which of course contains the open string homology. So therefore, these things here in particular contains amplitudes involving one physical open string, which is selected by this P0, an arbitrary number of the forming closed strings. So these abstractions are saying that this amplitude should vanish. So that's the physical condition for the existence of the vacuum shift solution. So we can have an effective field theory description of this. We can integrate out classically everything which is outside the kernel of L0, and then we can run the homotopy transfer and end with some effective action involving couplings of open and closed strings. So this was done explicitly by these two, independently by these two groups last year. So here I'm just taking the result. And so just note that these are the effective products that have entries in open strings, but also you can have entries in closed strings. And if you don't have entries in open string, that means that this is a zero product. So this is the tadpole. And in fact, the vanishing of this tadpole is precisely the same as the vanishing of the abstractions that we saw before. So if this tadpole is this massless tadpole, let's say this effective tadpole vanishes, then this psi naught is just the vacuum shift solution that we have discussed before. And so you see that in the effective action, you also generate this cosmological constant that is non-dynamical. So let's have a look more closely at the shifted theory. So the theory expanded around the vacuum shift. Of course, we will have this constant part, which is the same that we get in the effective action factor, which is non-dynamical. And then we get again, this Witten theory, but with a new BRST operator. So first of all, what is the form of this cosmological constant? In fact, it's a sort of resummation of all the possible clustering amplitudes of the disk weighted by the clustering deformation. So this doesn't contain open string variables, so it's non-dynamical in this sense. And so the first dynamical object, which is very important, is this bilinear, is the BRST, is the deformed BRST operator, which contains this correction from the vacuum shift solution, which essentially deform the kinetic term by giving mass corrections. Okay, so this is concretely how the deep brains adapts to the new background given by this clustering deformation carried by E. So let's see these things at work with an explicit example. So let's take a D1 brain, which is wrapped at the self-dual radius. We can consider deforming the Witten theory of this on this D1 brain with this Elwood invariant, which is built essentially with the YY component of the graviton. So this, in fact, is the so-called radius deformation, because this is exactly the vertex operator that controls the length of the compactification radius. Now, so you immediately see, because these are two U1 currents, they just have a double pole, but they don't have single pole, and therefore this condition is satisfied. And in fact, this means that the D1 brain can adapt to a change in the radius. This is, of course, what you would expect. You can consider another exactly marginal bulk deformation that is a little bit more strange, which is this one, which is composed with these two SU2 currents, that one is sine, the other is cosine. Now, this is from the bulk perspective, this is as good as this one. They are both exactly marginal. They are related by global SFT transformation in the chiral and antichiral part of the CFT. But once you have the boundary, then you can run into trouble, because with Neumann boundary conditions, then these two guys, of course, have non-trivial OPE, because these two guys closes on this thing by the SU2 algebra. And therefore, P0E now is non-zero. And you see precisely that is in fact an element of the Gauss number 2 closed string cohomology. So therefore, that means that the one brane cannot adapt to the deformation carried by this thing. So let's continue to see what happens with the radius deformation, which is something that is not abstracted. So we can look at the mass deformation. We can look at what happens to the initial massless fields on the D1 brane. So when you were at the self-dual radius, we had these three massless fields that together they form this, they are tangent to the SU2 moduli space of the D1 brane. And now we can compute the mass correction with the formula we had before. And so this corresponds to these open closed amplitudes involving two open strings, a propagator and a closed strings. And so let's see how they are. So explicitly, they look like this. So they are explicitly given by worksheet in some sort of complicated geometry given by width and vertices and propagator. So it is known in general that these complicated worksheets can be mapped back to the upper plane using Schwarz-Christoffel map, but typically these transformations are highly transcendental and complicated. So in this case, there is a shortcut that we can use following and adapting what was done already by Berkovits and Schnabl back in 2003 when they computed the quartic potential of Jan Mills using analogous methods. So, okay, so now I think I don't have enough time to explain all the computations, so you can read it in the slides, but essentially there is some algebraic manipulation you can do using the Hodge codire decomposition and many other tools to completely smash this complicated geometry in something that is in the upper half plane with no more U operators. Okay, so this is really an upper half plane correlator. Now, the next thing is that you have to put an epsilon here on the L naught in order to control possible divergences coming from the collision of these two open strings. So here we are in the bosonic string, so there can be tachyons, and there can be, in particular, objects that have negative weights, and therefore you want to be sure that you use a parametrization of 1 over L naught that converges when it acts on negative weight states. So this is precisely the problem of collisions, and which is tamed exactly by this epsilon, because the idea is that now you compute this correlator at finite epsilon, you get something that depends on epsilon, then you set epsilon to 0, and this is the correct restriction. So in total, this mass correction, they all look like this. So you see they are very simple correlation function of 4-point function in the matter sector with this epsilon prescription to cure problems from open string degeneration. And so now you can just compute it for the U1 current that should remain massless. And you see that they indeed remains massless, because in fact this integral gives you, so this integral would be divergent because of this open string divergence, but this epsilon regularization gives you this result here, and in total you get 0, which is what you want. On the other hand, the other SU2 currents, they get mass, as they should, because they are no more moduli. They will be lifted by the radius deformation. And in fact, they are lifted. And again, the same kind of computation now gives you a finite result. And then you can match, thanks to this result, you can match mu with the variation of R by looking at this mass correction from the KK spectrum, and you can exactly match how much the open string field theory parameter is related to the physical change in the radius. Okay, so this was how more or less the story is working for the bosonic string. So let's see what we can say for the superstring. So we will only talking about NS open superstring field theory. So we just talk about this in large hyperspace, where we have two nilpotent commuting derivation, Q and eta. And this is the form of the action, which here I write in fully expanded form, because that's what I'm more interested in, because I'm doing like a sort of perturbative analysis. So you see we have a kinetic 10, we have a bunch of non-polynomial interactions, and then we have again this open-close coupling. Again, this open-close coupling is gauge invariant if this E is in the small Hilbert space and it's killed by Q, and then of course it commutes with the star product essentially. Again, we can play exactly the same game. So we can write the tupple source at the equation of motion. Now this source is more complicated. This interaction part is more complicated, of course, because the theory is non-polynomial, but the strategy is exactly the same. You're going to solve it perturbatively, so you get order by order a different equation. And you see the first equation you get is very similar to the one that we were getting for the bosonic string. And so let's see how we are going to construct this vacuum shift solution. Again, perturbatively, we can write phi 1, phi 2, phi 3. So these are at higher orders of mu in the closed string deformation. You see they are all sourced by higher powers of the closed string E. And so here the difference with respect to the bosonic case is that we have two homotopy operators, like two propagators, and one is the one that we have already used, that is the homotopy operator for Q. And then we have a dual homotopy operator, which is H tilde, which is perfectly parallel to it, and which obeys parallel properties, in the sense that it obeys an Hodge-Kodaira decomposition with eta and not with Q, and it is killed by Q. So this sort of lives in a dual small Hilbert space, and it is the and it is the homotopy field of eta. So this structure was also observed some years ago by Kreuter, Okawa, Schnabl, Tori, and Zwiebeck in the BV analysis of the Weizmann-Witten theory. And the full propagator, I mean the inverse of the full kinetic term, is of course given by the product of these two homotopy field. Now again, the usual story that we played for the bosonic string applies here as well. So these are not full solutions. So here we have only solved the equation of motion outside of the kernel of L naught. So we have to see what happens inside the kernel of L naught. And inside the kernel of L naught, we get these obstructions. So this thing should be 0. Okay. You see again, this again looks like a large Hilbert space amplitudes between a physical open string, which is captured by this P naught, and n deformed closed strings according to the order we are. And notice that these amplitudes have an explicit H tilde symmetry, which is the same symmetry that was in the original action between Q and eta. In fact, okay, so this looks like that. So there should be a sort of double homotopy transfer to understand this perturbation theory, which, however, at the moment it's not clear, at least to me. So closed string deformed action, effective action in the large Hilbert space. So we don't have at the moment this homotopy transfer package, but still we can integrate out by hand and see what happens. So we can do it. It's just you sit down and do it, and then you get this effective action for phi. So here phi is in the kernel of L naught, and E is the deforming closed string. So here you see the first line, so we get a non-dynamical cosmological constant. In second line, we get this effective tuple, which is in fact just the same as the obstruction we found in the previous slides. In third line, we get the mass deformation, and so on and so forth. So these effective couplings now can be computed in complete analogy to the bosonic case by flattenization of the Witten diagrams to the upper plane, essentially redoing what we did in the bosonic case, because the conformal structure is exactly the same. So the Witten product is still there. So you just have different insertions. Well, you can do this, but here in the superstring, in fact, there is something that is very nice. Sometimes this superstring setting allows for drastic simplification, and in fact, this mass term often they can be computed via localization at the boundary of the worldsheet moduli space, as we are now going to see. So, okay, from now on we are working at strict zero momentum. So, in a sense, we were interested in understanding the algebraic effective couplings in the. So that's the story. So usually in superstring background, the matter boundary conformal field theory has an n equal to superconformal structure, and the massless states can be decomposed according to their n equal to r charge, so belonging to a part in the chiral ring and a part in the anti-chiral ring in this way. So this G is the n=1 supercurrent that splits in the two component in the plus minus component of the n=2 supercurrents, and this V1/2 plus minus of the BPS states that are killed by the other, plus kills minus and minus kills plus. The same has to be assumed for the clustering. So in this case, we are considering an SMS deformation, for which the chiral and anti-chiral part of the clustering also belong to these chiral rings of n=2, and so they have a definite charge. So in total, the clustering can be written in this form according to the decomposition of the R charge of these two supercharges. And so if this decomposition holds, then the effective tadpole is vanishing to first order, and also the cubic open string coupling vanishes. So these are two good news. So this is guaranteed. So it is guaranteed that the vacuum sheath is unobstructed, at least to first order. And also, you know that you don't have cubic interactions between the massless states that have this decomposition. So the first non-trivial coupling you get in the effective action is just the master of these 5 fields with the clustering. And this is a very similar computation we already did for the bosonic string. But now we can see the power of localization, because this 4-point function can be completely localized at the boundary of modular space just by playing some tricks. For example, here you take out some Q, here you take out some eta,
Carlo?
you do some massaging.
You
Hello?
have 5 minutes.
Okay.
There.
Thanks a lot. And so you see that at the end of the day, you rewrite this 4-point amplitude as something that only contains P0 and doesn't contain anymore the propagator. So P0, in fact, projects at the boundary of modular space, right? Because the way to understand P0 is this thing. So this is a very long open string strip. And so therefore, these are in fact 2-point functions. These are no more 4-point amplitudes. And we can see this thing explicitly. So these 4-point amplitudes becomes 2-point function. And so they really becomes like this. Where these G and H fields are precisely computable from OPEs of the G's from the deforming clusterings, and for the V, and for the H for the physical open strings, and so you can then you can combine this with the quartic potential that you get only with open strings. This by analogous method was computed some years ago by a student of mine. In 2018, Alberto Merlano, and so we can put these things together, and then we get this nice potential that is a sort of a sum of perfect square plus again a shift that is going to compute the energy of possible bound state that you can form. But you see that now you can find minimum of these potentials since these things are positive definite just by setting these things to 0. And in fact, this precisely corresponds to the deformation of the ADHM constraints in a generalized setting by clustering fluxes. Okay, so in the paper, we have analyzed the construction of Nekrasov non-commutative instantons, taking the D3D-1 system and deforming it with the Kalb-Ramond, constant Kalb-Ramond field. Okay, so it all fits in this setting. Okay, so maybe here I can skip because I don't have so much time. So we can, so I said that with the Wezumino-Witten theory, we didn't have a full all-order results because we were lacking of a complete understanding of the homotopy transfer. On the other hand, if we formulate the theory in the small Hilbert space, we have a nice construction. And so in this case, everything can be put in a infinity form, which is also cyclic, and therefore the standard formula for homotopy transfer can be derived, and you end up with the closed form expression in coalgebraic way of these open closed couplings that can be then expanded to the order you wish and find all the possible open closed amplitudes that you want on the disk, of course. And okay, let me just state that this effective theory is in general different from the one we get from the Wezumino-Witten one, because the two theories are related by Fourier definitions, and therefore these are also the effective actions will be related by Fourier definitions in a sense. But what is important is that they have the same vacuum structure, and therefore the results on localization are the same. Okay, so let me come to the last part of the talk, which is also something I think very important. Is less formal and more physical, I think. And it's about clustering degenerations, okay? So here we are controlling everything with open string propagator. So diagrams with 2 or more closed strings, in general, we have regions in modular space where closed strings can collide, okay? This is a clustering. So similar things, so we've seen similar thing happening for open strings, but then we saw that doing this treatment of the open string propagator and correctly treating the epsilon going to zero limit was saving the day. Now Witten vertex and propagator now cover the whole worldsheet modulo space, but on the other hand, it does not give an obvious regularization towards closed string degeneration. So let's see explicitly what happens, for example, for the radius deformation. So this is the first term in the cosmological constant of the radius deformation. So this corresponds to a disk bulk 2-point functions. So the diagram is like this. It can be flattened down to the upper half plane with the usual techniques, and you end up with something that looks very innocent and nice. But you see that here you have a 1/t² divergence. This is the open string degeneration. This is cured by this epsilon of the propagator. But here you have this 1 - t⁴ that is partially cancelled by the Gauss contribution model completely. And this is not protected. Okay, so here you don't have anything in principle to deal with it. So what to do with this divergence? Okay, so the idea is that since this is closed string degeneration, it should be regulated by a closed string propagator, just like open string degeneration is regulated by open string propagator. And right, so here we are in a purely open string theory, so it's not obvious how you get a closed string propagator. But okay, in this simple example, you can essentially be you can essentially be guided by this formal identity. So that's an identity. In fact, that's the same amplitude written in two ways. The first way is just the closed string propagated by the open string propagator and hitting another closed string. And these other one are two closed strings acting on the SL2C closed string vacuum propagated by the closed string propagator and then hitting the boundary state. Okay, you can check explicitly that by doing the conformal map from the disk to the upper half plane, essentially, that these two things are exactly the same. And in fact, you can precisely map the Schwinger parameter of X with the Schwinger parameter of T in this way. So this is just a fact, okay? It's nothing fancy. But based on this fact, then you can say, wait, okay, now it's clear what I have to do, because here the dangerous region will be x = 0, that corresponds to t = 1 here. And now, of course, x = 0 is regulated by this 1/L0. I put an epsilon here. So I consider the regularized closed string propagator, and now I get a final result. And if I do this, now this amplitude is precisely 0 for the radius deformation. Now, the fact is that we don't really have something to compare it with, and also this derivation is a bit heuristic. So we decided to, after following a suggestion by Ashoke, we decided to compute again.
In principle, yes, your time is up, so it would be nice if you can wrap it up.
I'm really over. So we redid this computation with open closed string field theory. Essentially, now here we get two contributions. Now these two contributions nicely match together, given exactly the same change of variable. And we can regulate the open string stubs, and we can connect the open string stub and closed string stub in such a way that these two diagrams cover the whole moduli space. And so we give a sort of rigorous derivation. So let me just go to the conclusion. So open string field theory based on Witten product allow for explicit perturbative and non-perturbative computations involving open and closed strings, and all computations are fairly explicit to the very end. So now I have some pressing questions. So I already alluded to this. Is there a large Hilbert space homotopy transfer? Now, positive evidence in this is so you can see there is some sort of homotopy transfer in the partially gauge fixed Wezumino-Witten theory. So this is some work in progress. Another thing, can we systematically control closed string degeneration inside open string field theory? So is it useful to understand open string field theory as a singular limit of open closed string field theory? Again, related to this, sometimes amplitude localizes also on closed string degeneration, okay? Because this localization at the boundary of moduli space, it also includes closed string degeneration. So can we understand this in open string field theory? Perhaps we can also understand localization in open closed string field theory. And then I have other questions that are maybe a question for people in the audience. Okay, so can we consistently couple the Gauss dilaton? So this is not a 0-0 primary, so it's not obvious how you use it in this setting. And also, what is this cosmological constant computing, which is a little bit unclear. So, so you see there is so much to do, and thanks, and comments and suggestions are welcome.
Right, thank you very much for this talk. Let's thank you virtually, or we have time for questions now. So if you have a question, please raise the hand. Any questions? Questions? Everyone is shy, apparently. Maybe I can ask a very naive question. I must admit, for me, it was a little fast, but you were talking about needing some notion of double homotopy transfer that you didn't have. Could this, I mean, this is the most naive question you can have. Could this be related to what people call double copy?
I'm not sure. So this is really related to the fact that you have this large Hilbert space and you have two kinetic operator that is not homology unless you go to the small Hilbert space of the other operator.
Okay, it's not. It doesn't sound.
I don't know. No, I don't think
you
it's
never know, but
double copy. Yeah.
Okay. Any other questions? Okay, if not, let's thank Carlo again. And then we'll have now the panel discussion. So my understanding is that Nathan will run this.
No, I'll go first, but I won't run it. But
Sorry?
I'm not going to run it.
Well, I'm certainly not going to run it, but so I introduced the panel discussion. I don't know how it will go in detail. So I assume
I can go first, but
yes. So Nathan will go first, and I was asked to remind everyone that we'll take a picture afterwards. So please stick around for the picture. And so Nathan, please go ahead.
okay, thanks. So thanks for the to all the organizers for organizing this workshop. So I guess I saw this as a homework exercise that I thought I couldn't do, but so the homework exercise is to try to find an application of string theory outside of string field theory outside of string theory. And then I realized that I was actually working on a project which does this. So so together with Karim Benakli, he's a researcher from Saclay, and Cassiano Daniel and Mateus Liz, I attended a seminar of Karim, who's a phenomenologist, and he talked about problems with constructing Lagrangians for massive spin 3/2 charged fields. So of course, there are no fundamental massive charged spin 3/2 fields that we know, but there are composite charged 3/2 fields that in the low energy limit can be treated as a fundamental object. And I had worked on free massive spin 3/2 20 years ago with Marcello Lecce in string field theory. So it's just, this at the first massive level in the superstring, you have massive spin 2 and massive spin 3/2. So it turns out that Argyres and Nappy had done massive spin 2 in string field theory, I guess maybe 15 years ago. So charged massive spin 2, just to write down how it couples to the electromagnetic background. So what you do is you just modify the boundary conditions like in Born-Infeld. So you have massive spin 2 in with the boundary conditions of just a U1 field. And you just use normal string field theory and compute the kinetic term. And it's not so complicated, but there are all these auxiliary fields, and well, it has an interesting answer, and people used it to describe massive spin 2. It turns out that in 26 dimensions, of course, the answer is simpler. And when you compactify to 4 dimensions, you get some extra scalars coming from the compactification. And together with this group, we used the hybrid formalism, so which is the 4-dimensional version of the superstring in which you have manifest n equals 1, d equals 4 supersymmetry. And we just looked at how the spin 3/2 comes, and it's not simple, but it seems to give an interesting answer that seems to be useful for these field theory people. So so that's an application of string field theory. So it's just string field theory has a nice way of describing massive spin states. Okay, but I hope I still have a few minutes. I want to provoke people because I tried to provoke Chien and he didn't seem to take the provocation. I think people are not doing superstring field theory. I think they're doing spinning string field theory. So I mean, spinning string is interesting. It has tachyons. It has, I mean, you can describe some nice backgrounds, but they're not really the interesting backgrounds. The interesting backgrounds are the supergravity backgrounds. And I don't understand, I still don't understand why he didn't take the provocation. And Ashok made a comment that I also didn't quite understand. I don't understand why the superstring Ramon background should be more complicated than the flat background from a string theory point of view. So, I mean, we can certainly describe PP waves. Nobody complains about PP waves in Ramon background using string field theory. And nobody claims that's not string theory. So why do people claim that Ramon backgrounds is not string theory? So, okay, so that's my provocation to people. So I'll stop and go to the next person.
Okay, I think we're going to alphabetical order, so it should be me. So let me start share screen. Okay, so this is supposed to be a string field theory beyond string theory, but I'm afraid my comments might be within string theory, and I'm sorry about that. But then I'd like to mention some directions which have not been explored much in the past conventional research of string field theory, so I hope you enjoy it. So at the string conference, Bart and I led a discussion session of the on string field theory. And I talked about homotopy algebras, in particular, homological perturbation theory. So this is just the infinity version of the beautiful lectures by Olaf, so I don't think we need to repeat it today. So so what I wanted to say today is that then, the following. So Olaf told us that we can construct infinity algebra for any theory, any decent theory. On the other hand, the stringy realization of the homotopy algebra, which is based on the decomposition of the modular space, seems to be very powerful. Actually, so the homotopy algebra we usually define for example, for the scalar field theory, it looks rather trivial. So on the other hand, this stringy realization of the homotopy algebra seems to be very powerful. And then we feel, or I'm not sure if you agree with me, so I think I should say just I feel, but then this stringy realization uniquely determine the theory up to field definition. That's I think some of us believe. So I'm wondering how we can characterize the stringy homotopy algebra. Furthermore, if the low energy effective action, effective theory, like the one described by Carlo in the previous talk, so if it inherits the stringy homotopy algebra via homotopy transfer, we may be able to investigate the low energy effective theory using the stringy homotopy algebra. So this might provide us with the homotopy algebraic approach to the Schnabl program. This is one thing I wanted to say. And one more slide from the string conference. So which is about the ADS-CFT. And some of you already heard this story several times, so I don't want to repeat it today. But let me just tell you one thing, which is the following. So whether you like my approach or not, the gauge invariance of superstring field theory at the quantum level should be an important issue for everyone, right? And to me, the gauge invariance of the open superstring field theory with source terms for the gauge invariant operator at the quantum level is most important. And this gauge invariance of superstring field theory at the quantum level is closely related to the so-called spurious singularities in the superconformal gauge sector. And Sen and Witten told us what to do if we encounter such spurious singularities. But then it is difficult to tell when we encounter them. So this is actually something we already discussed several times during the discussion session of this workshop. And this is very difficult problem. On the other hand, in the case of the bosonic theory, there was a beautiful proof based on the beautiful proof of the gauge invariance at the quantum level based on the minimum area metric. But this it may be difficult to generalize it to superstring because we no longer use the idea of length or area in that case. So I'm very curious about the alternative possible approach based on the supersymmetric generalization of the hyperbolic lattices briefly mentioned by Barton. Okay, coming back to the ADS-CFT. Yesterday we heard a very nice talk by Rajesh, and maybe the most difficult things about the deriving the ADS-CFT is the equality of the theory with the holds and the theory without hold with the back-reacted geometry, this equality. And we need to sum up all the holds. So the last thing I wanted to say is that to sum up infinitely many holds, I'm wondering, it might be useful to use the homotopy algebra to organize Feynman diagrams. So this is a nice figure I took from the paper by Saemann, and so I think I should do this. So this is the very nice figures from this paper by Saemann and Lagrangians. So in this case, so this kind of loop diagram can be written, organized this way. And this is algebraically something like this kind of geometric series. So we have more algebraic control over this Feynman diagrams. So anyway, so this kind of direction research can be fruitful interaction between various fields like field theory and string theory. So I hope this can be good. So we expect an interesting collaboration to occur. So this is that's all I wanted to say. Thank you. So it must be Schnabl, Schnabl Sen. So it's so I think it's Martin, right?
Okay, so should I go on?
Please.
Yeah, okay. So I'm sorry, I'm using my cell phone because the integrated camera on my laptop stopped working somehow yesterday. Well, okay, so I was thinking about what to say, and of course, the easiest thing for me is to talk about things that I've been thinking about recently, because it requires essentially zero preparation. And well, the topic that we were suggested by the organizers to think about is the applications of string field theory. And I was always somehow like amazed how string field theory knows about different boundary conditions in conformal field theory. And I started to think recently about this from a different perspective. And with my student, Maki Kuderna, we realized that actually the same story repeats in the very ancient 20 years old vacuum string field theory. And essentially in vacuum string field theory, everything factorizes between ghosts and matter, and then you can forget about the ghosts and you can forget about the auxiliary CFT. So then it becomes a problem only in the matter CFT of your interest. And then that essentially you get some sort of bootstrap conditions on the structure constants of BCFT, and that's what string field theory is using, at least the vacuum string field theory. So so I think this answers Shi Yin's question, but I think he's not attending this panel discussion, which is a pity, otherwise he would have been pleased. But I think that's why string field theory is so powerful, because even its cousin vacuum string field theory knows about these boundary conditions. So the second thing I want to touch upon are classical solutions in closed string field theory that I've been thinking on. So in the past 2 years, people in our community realized why do these homotopy algebras, how do they appear naturally as effective actions when you integrate certain fields? It's very natural. And the closed string field theory, as was mentioned in talk by Ted, also has this sort of structure. I mean, there is not much difference between the homotopy Lie algebras and homotopy associative algebras. So one would think that these come from some bigger parent theory after integrating out some degrees of freedom. And that's what I've been thinking about. And I don't have the details to show. I mean, I didn't have the time to so. But I think if we somehow work create like a vacuum string field Tanaro for closed string field theory, it's just a model. I'm not saying that we have honest derivation from first principles, but let's think about some vacuum string field theory for closed string field. And if you go to this parent theory, which is cubic, from which you get the L infinity structure by projecting out certain fields, etc. And well, you have to be clever about ghosts. But then in the matter sector, you very naturally get something like that the solutions should correspond to projectors. And what you naturally get is that the solutions of closed string field theory correspond to defects separating two theories. And it leads me to this conjecture that I can now say what the action of closed string field theory calculates. So the conjecture is that the action of closed string field theory calculates the G function of the defect which separates the two backgrounds, the starting background, the reference background, and the background that the solution is describing. Of course, there is this issue. Well, there can be several defects separating two different backgrounds. So which one do we get? And I still don't have a good answer to this question. Okay. And also let me make a point. Also, this there is this famous solution like this like the tachyon condensation on the orbifolds that was studied by Yuji and Barton in closed string field theory. And so this theory it differs from the standard theory in, let's say, flat space just by the action of topological defect, or that exists topological defect which interpolates between flat theory and C mod Zn, or for any two ends there is a topological defect between the two. So I think the hint is that actually there should be a topological defect, but I'm not so sure. But yeah. Okay, let me stop here. I think I used my 5 minutes. Thank you. So now I think Ashok should be.
Okay, so thank you. So I was asked to say something about application of string theory outside string theory. So what I'm going to do is to describe an application which is, well, strictly it's outside string theory, okay, because it's in two-dimensional conformal field theory, although perhaps not everybody would think of this as a really different. Okay. So let me just share my screen. Okay, can you see this? Let me full screen. Okay, so this basically follows what C told in his talk. Okay, one of the topics that he touched upon is string theory in RR background. Okay, and maybe I'll come back to Nathan's provocation at the end of this talk. But what I'm going to say today is related to this, okay, but in a much simpler context, okay, that we can also apply the same method for studying string theory in NSNS background. And these deal with marginal deformation of worldsheet CFT. Okay, the same kind of techniques that he described, okay, we can use to describe marginal deformations in worldsheet CFT. Okay. Now, normally you don't need string field theory for this. We use conformal perturbation theory. Okay, imagine that you have some point in the moduli space of a CFT where you can solve the correlation functions exactly, and then you want to do some marginal deformation, you can use perturbation theory. Okay. So you can use this, for example, for computing the shift in the conformal dimension of operators or OPE coefficients. Okay. But to do this, we have to study correlation functions with multiple insertions of the marginal operator, typically. Okay, and you have to integrate over their positions. Okay. And whenever you encounter this problem of integrating over positions of operators, we know that you run into divergences. and they need to be regulated. Okay, you can get divergence when the marginal operators collide with each other, when the marginal operator collides with one of the vertex operator whose conformal dimension you are trying to calculate, or in a more complicated situation, the marginal operators, two marginal operators may approach the vertex operator simultaneously, and so on. So this becomes a complicated problem at higher order. Okay, even though in principle it can be solved. But we also have to keep in mind that different kind of regularizations may give different results. Okay, and this, of course, we are familiar with in normal normalization. Okay, it's called scheme dependence. But you also know that this corresponds to redefinition of the parameters. So in this case, it will be redefinition of the deformation parameters. But one complication that one encounters here, okay, is that you have to be very careful in using the same regularization, okay, whatever that means, for all computations. Okay. In other words, if you want to calculate the renormalization of the 2-point function, okay, say renormalization of the conformal dimension, you use the regularization. If you want to calculate the renormalization of the deformation of the OPE coefficients, you will use the regularization. And they have to be the same, okay, as I said, in whatever that means, okay, because the diagrams are different. But otherwise, different quantities may be expressed in terms of marginal parameters that are related by some unknown redefinitions. So 2-point function may be expressed in terms of one set of variables. Okay. The 3-point function may be expressed in terms of another set of variables, and they may be different from each other. So all of these problems, okay, can be resolved using string field theory. Okay. String field theory does not suffer from this problem. Okay. So the idea is that you simply describe the effect of marginal operator as some classical solution in string field theory, and you use that deformed classical solution to do all your computations. Now here, of course, we do have a choice of which version of string field theory you use. Okay. And these different choices are related by field definition. Okay, and as a result, they correspond to reparameterization of the deformation parameter. But once you have chosen a particular string field theory, then everything can be computed in that string field theory without any further ambiguity. Of course, the original string field theory has to be consistent, which means that it has to be based on some underlying L infinity algebra, for example. And after that, there is no further ambiguity, and all quantities can be manifestly finite, and they can be expressed in terms of the same marginal parameter. You don't have to worry about whether you are using the same parameter for different computations. And a prototype of this calculation was done some time ago, but that was just the beginning. Okay, I think there is a lot to be done here. Okay. So let me just end by saying describing a possible application. Okay. And that is in studying the spectrum of operators and OPE coefficients in 2-dimensional n equal to superconformal field theory with Calabi-Yau target space. Okay, this is of course important for string theory, but this question can be formulated purely in the language of conformal field theory. We just want to calculate the spectrum of operator dimensions. Now, this, of course, we know this difficult task at a generic point in the moduli space, okay, except maybe for spatial quantities which are topological. But we can compute them at spatial points like orbifolds or Gepner points, okay, where this theory is solvable. So any correlation function in principle can be computed. So here we can start at these points and then explore the neighborhood using marginal deformations. So for example, we can use the blow-up modes of orbifold points to explore the space around the orbifold points. And because in the language of string field theory, you do not encounter any divergences, in principle, we can write a computer code to do these computations to any order in the expansion of the deformation parameter. Of course, the computations will become more and more complicated, okay? But the absence of divergences means that you can completely codify it. Okay? You don't have to actually do the calculation by hand. Okay, so that's the end of my presentation. Okay? Now, let me just say a few words about what Nathan asked. Okay? So Nathan asked about Ramon background. Okay? So I think what she was saying and what I also want to emphasize is the following, that I think if you are working for a generic point in the moduli space of CFTs, okay, then neither Ramon background nor NSNS background can be described exactly. Okay, at a generic point, you don't know how to solve the CFT. So you have to start from some particular point and then deform. And what NSR formulation, the limitation in NSR formulation is that the starting point should only have NSNS back. That's in a sense, it's in a sense you can say it's not a fully background independent formulation. The starting point should have NSNS background, but then you can deform it either by choosing RR background or NSNS background, right? I think at the level of string field theory, I don't see any difference. That whatever C was describing for Ramon background is exactly the same technology that will be using for NSNS background. So I don't think there is really any difference at a fundamental level between Ramon and NSNS background from the perspective of string field theory. Okay, I think I'll stop here.
So I think the idea now is to open the discussion for the audience, and they can ask the panelists can ask each other or provoke each other. Or it's up to you.
So can I ask Ashok?
Sure.
Yes.
So, well, there is a difference, right? Because of the different dilettante dependence, right? So Ramon. So you're assuming when you say conformal field theory, I guess you mean n equals 1 superconformal field theory, right?
Yeah, if you are doing string supersymmetric string theory, yes.
But I don't think that's the correct. So in that formulation, Ramon backgrounds look very different, right, from Nevershort's, because because you have to get to ADS5 times S5, you need an infinite Ramon, right? Because of the extra dilettante factor. Suppose we're at small coupling.
Okay. So as I said, ADS5 times S5, nobody has done. So I don't know how to do this, but let's go to the calculation that has been done, okay, which C described. ADS3 times S3. Okay, times you can use T4 or K3. There you start with a background which is NSNS. Okay? But then you can switch on RR flux. And that you can treat perturbating, okay, by using this marginal deformation techniques. Okay, it's not called marginal deformation of the CFT, but as far as string field theory is concerned, okay, it's tree-level string field theory you can use for this computation. Of course, you can go beyond if you want. Right? You can start doing loop calculations also, but at tree level, you can study the effect of switching on Ramon flux.
So you say no, but sorry, you're doing ADS3 times S3 with Ramon flux, so that's no longer a WCW model.
The starting one is NSNS flux.
Yes.
Then you switch on Ramon flux as a deformation.
Right, but are you trying to preserve the supersymmetries or not, or what?
Yes,
I'm not.
It's the standard ADS3 times S3 with Ramon flux.
Yeah,
Together with the NS flux. Okay, you start with the pure NSNS flux.
Yeah.
And then you describe the Ramon deformation by switching on Ramon fields.
I'm happy that you can describe it perturbatively, but I don't think you can get to the finite. We can describe Calabi-Yaos. We don't have to describe them perturbatively. We can write down the sigma model for the Calabi-Yau.
Yeah, but nobody knows how to do any computation there, right? I mean, if you really want to describe Calabi-Yau, you start with some point where you know how to do computation and then you deform, right? That's the point I was trying to emphasize.
Okay, but then, so PP wave backgrounds, right? We know how to describe PP wave backgrounds. We know how to do computations, right?
Yes.
And they're not covered by your perturbation theory, right? There's no way to describe.
No, actually, if you look at our paper, we exactly describe PP wave background.
How can you get to PP wave if you only describe?
We start with a flat background, and then we again describe the Ramon fluxes as the Stringfield solution, and then we get the agreement with the Green-Schwarz.
PP wave is like, you claim you can describe Green-Schwarz by perturbation theory?
No. Okay, so the way people dealt with the PP wave background was by, in the Green-Schwarz formalism after suitable gauge choice, it reduces down to some free theory at the level of the worldsheet. And that's how people were able to get the spectrum of the PP wave background. And basically, if you do this usual NSR formalism, you start with a flat background, and then you find the Stringfield solution corresponding to turning on this Ramon flux. We did this computation explicitly, and we got the agreement.
Okay, all I'm trying to say is I don't think PP wave backgrounds is an n equals 1 superconformal field theory. So I don't see how you can get it from.
No, I mean, the Stringfield solution, when you deform by the round plus background, is nothing like local quantum field theory anymore. I mean, the closest that we can say is that it's some type of non-local conformal field theory, because we have to add like, pairs of like round vertex operators because they're in the half integer pictures.
Okay,
So it's not the usual local.
I disagree. I don't think you can describe Green-Schwarz using half integral.
No, Nathan, I think that there is a difference. I mean, you're thinking of the starting point, right? The starting point for them is free string theory, flat background.
Yeah.
But now you can, not every solution of string field theory is 2D CFT, right? Precisely because of this, that you can get solutions using Ramon background, because those are fields in the theory, right? See, if you have a field theory with a set of fields, you can certainly look for solutions where those fields are non-zero. Right? I think that's the philosophy that they take. Not that you try to write down a sigma model for that background.
Exactly.
So you claim you can reproduce the standard PP wave computations using perturbation theory around the flat background.
Yes, we did. We get the exact agreement.
Okay, I'll look at those papers.
Yeah.
No. Okay, thanks.
Yeah, and also another thing is that, I mean, if you look into the paper, it has no problem describing, both turning on NS and Ramon backgrounds in the case of the 3 flux. So yeah, the approach is pretty straightforward. Yeah, all one is doing is simply finding solution to string field equations of motions. And this is good thing because typically people say words like, the space of string theory that we can formulate is like, space of some Walshy CFTs. But I mean, in a sense, we are trying to say that maybe we can go more, like you can consider all those Walshy CFTs, but also you can consider the string field equations of motions written down around each of those Walshys, and then you can try to look for solutions. Then you might actually land on something that you didn't expect before.
So you should be able to get the 10-dimensional supergravity equations. Is that correct? You can get them from perturbative RNS, the supergravity.
So that's a good thing. So basically, at the very first order in the Raman flux deformation, the equation we get is exactly that. Once you turn on Raman flux, it requires you to turn on NSNS part of the string field, which is exactly Einstein equation.
Yeah, so you can get them only when the flux is small, but how do you get the full supergravity equations of motion?
I mean, yes, we are not, okay. I mean, we were already, again, we were working productively in the Raman flux. We are not claiming that like we have the result for some finite RR flux. In the example of the PP wave that you just mentioned, if we just productively expand the RR flux background result, we get the agreement order by order in the deformation. And the expression we already know from the PP wave side is that, it is, I mean, if you, some of this part of the series, it converges to the exact answer. So of course it should work.
No, of course it should work because we know it's a consistent string theory, but I'm questioning if you can show, for example, the ADS 5 times S5 is a consistent solution of string theory. I don't think you can. You claim you can. You can show the ADS 5 times S5 is a consistent solution of the consistent background of string theory using perturbative RNS?
Okay, so let me put it this way. So we are not claiming that we know that ADS5 S5 with quantized RR flux is a consistent background.
No, not quantized. I'm not quantizing RR flux. I don't care about quantizing.
Okay, but order by order, we have no problem constructing string field solutions.
I'm asking a question. Can you show that ADS 5 times S5 is a consistent background of string theory?
I mean, order by order in the Raman flux parameter, we can.
Perturbatively, you can, not for finite R.
Yeah, we can.
Oh, you can for finite R.
No. We don't have any argument for finite radius. We are just saying that order by order in one over radius, we can construct this.
So you can't show that ADS 5 times S5 is a consistent background, and probably PP wave background. I don't know. Can you show that PP wave background is a consistent background?
Along the line you are arguing, we cannot. All we can do is to just order by order in 1 over R, construct
so
the
for me-
explicit
for
solution.
me, that's not satisfactory. That's not, I would like to do better. That's all I'm
But
I
saying.
mean,
the
it's
point
good
is-
that you would like to do better. I mean, I'm not saying that, we shouldn't try something like
Well,
better.
Green and Schwartz did better, right? Obviously, they
Yeah,
only
I mean,
did
we
it
are
in
just
Python
trying to
code.
demonstrate the idea because in the ADS case, there simply is no result to compare with. In the
I'm
PP
trying
wave
to say
case,
we
there
haven't
is.
solved the problem. I'm just trying to say we haven't solved the problem yet. Green Schwartz showed how to solve it in light cone gauge. We
Sure,
want
and
to solve.
in the PPA case, I completely agree. And in the PPA case, the reason why we tried was because there is an answer to compare with. But in the ADS case, we simply didn't any check that we could do
Okay,
because there was no
I'm
result.
very happy. I'm very happy with everything you did. I'm just saying there's more to be done. That's all I'm trying to say.
Oh, of course, I completely agree, and I will be very happy if someone actually comes up and gives us the okay, this is what you should in principle recover, and then we'll be very happy to match against the result. So yeah, I think there's much more to be done. I'm not saying that at the current formulation, NSR formalism is enough to describe everything we want with our flux. We are just trying our best, given what we know so far. So yeah, that's all.
Okay, thank you.
Yeah, thank you.
But also, Nathan, I just add that most of the string backgrounds, the interesting ones, right? The ones that will describe our universe, hopefully, at some rate, are of this kind. I mean, you cannot solve it exactly, right? I mean, if you have some Calabi-Yau or some moduli fixed at some arbitrary point, how do you study this? I mean, the only way I know is that you find a nearby point where you can actually solve it, and then you deform.
Yeah, but for example, Rajesh has this proposal for small radius,
So
right?
certainly for some special cases, I agree.
Yeah.
For some, those are special cases, right? And
They're
what you're
not-
saying is
they're
that
not
this
described.
general
I'm trying
method
to-
cannot describe those special cases. Exactly.
Right, but I'm trying to say that many of these special cases are not described as an n=1 superconformal field
I
theory.
agree. I fully agree. Yeah. So you are not saying that there is one formulation which describes everything, right? But in this formulation, you can go and you can explore things around it, which cover qualitatively all the features that you want, right? Including Ramon flux.
Right, but 95% of the work on superstring field theory uses the RNS formalism.
Yeah. Because their work is also for RNS formulation. But starting with RNS formulation, you can switch on Ramon flux. Right? That's the point.
I'm just saying that it might be useful for people to explore other versions of superstring field
I
theory.
agree. Yeah.
So
I'm not
topological
disputing
field
that.
theory, things like that.
Yeah. I'm not saying that superstring field theory is a solution to everything, right? It's a technology. And it can help us getting many useful results, right? It's not clear that this is the final story.
Yeah.
Yuji, you have your raised hand.
Hi. So Martin mentioned vacuum string field theory, and actually, when I was here in the talk by Ted yesterday, I also remembered vacuum string theory, and actually, I felt that his approach is kind of like a refinement of vacuum string field theory. But then I'm afraid that factorization of the matter and ghost sector can be realized in a very singular limit, but I think the limit is singular. So, but I think it's a good idea to reconsider vacuum string field theory at this point. It's just a comment. I just reminded by Martin's comment.
Yeah, if I can comment on this comment. So, so my student or my former student, Maciej, has started analyzing vacuum string field theory numerically. And it seems that there is just one overall scheme-dependent, sort of level-dependent regularization constant that is divergent. But if you sort of normalize things correctly, you can get really finite results. So for example, you can get the boundary state by just the analog, like just what we did for open string field theory, like calculate Elwood invariant for vacuum string field theory. You can do that, and you can get the boundary state completely unambiguously for string field theory, for vacuum string field theory solutions. So the theory behaves quite well numerically. except for one overall divergent constant. That's the comment to comment.
May I comment to comment? So what actually, sorry, it's not a comment, it's a question. So what kind of action you, Martin, and you considering?
So actually, we are taking the Siegel gauge action. Actually, we are not so interested in the action. We are just calculating the equations of motion. And the vacuum string field theory with the wrong kinetic term, which is given by just C naught, has the same Siegel gauge equations of motion as the correct one with C of I minus C of minus I. They both share the identical Siegel gauge sector equations. So then it depends in which framework you interpret your solutions. And the value of the action itself is kind of, there are some strange finite normalizations that we are obtaining, but for the correct sect, for the boundary state, we are getting unambiguous correct answers.
So you're basically considering the C naught for the ghost sector, or a Ci minus or plus or minus C minus I. Is that what you're saying?
You don't have to say which it is. I mean, it's actually the Siegel gauge projected. So it's like 5.
Yeah, but my experience is that the strict factorization between matter and ghost sector is rather singular. So it would be great. So some quantities can be calculated in the limit, but some quantity may not be very behaved very defined. Very defined. So that's why I'm asking.
Yeah, the theory is pretty singular, right? So normally you would think, well, you have a wedge state in the matter sector and wedge state in the ghost sector, and suddenly the things stop being associative and derivatives stop being derivatives, etc.
Yeah. So if you're expanding around your solution, and then consider the vacuum string field theory, in a sense, from the first principle, it might be very interesting, but it will be very difficult. Yeah. But but I think it might be good to reconsider this approach again.
Yeah.
Maybe Barton is trying to say something.
Yeah, just I was wanted to ask Martin a little bit. So the closed string analog of a vacuum string field theory, would that be a cubic theory? I'm not sure I heard well.
Yes, that's a cubic theory. So it's like the parent theory, which is cubic theory. So actually, we propose a form of a cubic theory, which is already of the vacuum sort of type, which has purely ghost kinetic term, and then we apply like the projections. Well, we have to do something with the ghost because normally we have this B naught minus on top of the Witten's product, so we have to we have to take care of this. It's a bit technical. And it's not, everything is not under 100% control. So that's why I placed everything.
But it's likely that once you expand around the conventional solution, the theory becomes non-polynomial?
No, the non-polynomiality comes when we sort of integrate out the extra degrees of freedom, or the extra components of the string field.
Oh.
Yeah. Well, if you start with Witten's theory, which is cubic, and you integrate out, let's say, some massive fields, you always get non-polynomial terms. So in this theory, so we integrate out fields which don't obey the level matching condition, among others.
Yes.
Both. Yeah. But the thing that really like gave me some important clue how to think about this is the ghost dilaton that we discussed yesterday. I think that's an important point for this procedure.
Yes.
So Martin, can I ask what your kinetic term is for the vacuum string field theory?
Who is asking, Ted? Or?
This is Ted.
Oh, yes. Well, it's purely ghost. It's anything which looks like anything like C0 plus in Siegel gauge. Yeah.
And the C0 minus is still there, right?
Yeah. So what we do is somehow uplift the theory. So we formulate the theory for string field for ghost number 3. Which is obtained from the conventional one by multiplication of C0 minus, and we get some different star product and things like that.
Okay.
Yeah.
Any time you're gonna be publishing some of this, Martin?
I don't know which journal will take it.
We look forward to see it soon. You can always just put it on the archive.
Yeah.
Then once it has 100 citations, any journal will take it.
And if I'm not doing, strictly speaking, string field theory, well, there are 2 points which I have been wondering. One is about closed string amplitudes. You know that the work by Amati, Ciafaloni, and Veneziano is resumming some partial closed string amplitudes, because the 3-level string amplitude is not unitary, because it violates the unitarity bound. So it is necessary to resum the string level amplitude, and they got it doing the aconal approach. So the question is there anything which string field theory can add on this approach? Because the main issue is that you violate the Froissart bond in closed string amplitude, scattering in the scattering. So this is one question which I have been wondering for a while. And the second is always partially connected with gravitation, is that when you consider a rolling tachyon, I would expect some gravitational waves emission. Can you get it from one loop string, open string amplitude? This is the second question which I've been wondering for a while.
Yeah, maybe I can say something that first of all, for this first question, yeah, I don't think so far string field theory can say anything about what this high energy scattering that you mentioned, okay? Because their analysis is really in the high energy limit. Whereas what string field theory does, I think, is so far, at the level of the amplitudes, is to make sure the infrared problems are taken care of. So at present, I don't think string field theory can give any more insight as to into the high energy scattering than what they have already done. That's as much as I can say about the first question. Second question, I think the best place to address this question maybe in the context of this matrix model that C was talking about, where you have basically 1 plus 1 dimensional string theory, and you have the rolling tachyon on the D0 brane. And that we know, I mean, in at least when the energy is very low, is indistinguishable from the usual closed string excitations. So that certainly is a avenue that one could try to explore, right? I don't think it has been explored yet by anybody. That how exactly the rolling tachyon matches into closed string radiation in that context, right? I think that is the best bet for as the first attempt to understand the relationship between the open and closed strings.
High energy behavior. There are two limits. There is the Regge limit and the Grosse-Mende limit. So would the Grosse-Mende limit be worth exploring in string field theory? Because it localized in some special point of a moduli space. So the question is, could be a good starting point, at least to get some hint to how the high energy amplitudes of shell look like. Just
yeah, I don't know whether that's a physically significant question, right? Off shell, because ultimately you really the on shell amplitudes are the physical ones, and my experience as far as the amplitudes are concerned, my experience is that if the worldsheet has given you some answer, okay, which is unambiguous, then string field theory cannot really add very much to it. When worldsheet cannot give an answer to a question, that's where the string field theory becomes important. Right? So in the Grosse-Mende limit, okay, that's my experience. Maybe others can add. I don't think, because they already have a well-defined answer, and I don't think the string field, using string field theory, you can get very much more information there.
May I ask a comments about the closing radiation? So this may not be a slightly different, but there was a, I remember there was a work by work on the imaginary deep range, which is can be interpreted as a closing radiation, right? So I think this might be some maybe something to do with the Eagle's question.
I see. Okay.
Let me try to
This
find
is
the difference.
This old paper by Lambert.
Gayoto Izaki Raseri, yeah. So
Oh,
I'm going to.
Yeah.
So I think this is very interesting, and then I wanted to revisit the question sometime. Yeah.
Yeah, maybe okay. A related question. I mean, again, in the context of this matrix model, the 1 plus 1 dimensional string theory, that we know this 1 plus 1 dimensional string theory should have the whole states, okay, which is absence of formulas, right? The formulas are rolling D0 brane, rolling tachyon on the D0 branes, okay? But there are also whole states which we know should exist from the matrix model perspective, okay? And their mass goes like 1 over G string, so they are natural candidates for D branes. But the question is how to describe it. Okay? And I think this paper that you mentioned, that basically takes imaginary boundary state, right? And that's the description. But one should really have a CFT description, right? I mean, what is the open string spectrum on these objects, right? And I think that's very difficult to answer by using the boundary state to the imaginary boundary state approach, right? So I think that is something worth exploring. That there's the open string description of these objects, the whole states. This is on the other side. I mean, when the energy is low enough, it should be closed strings. It should be indistinguishable from closed strings. And here the energy is on the other side, right? And or this absence of that those states. I think that's an interesting open problem, and it should be solvable by the current technology of open string theory.
There's also a kind of phenomenological meaning. If you believe that inflaton is a kind of tachyon which is rolling down, it is also some kind of phenomenological meaning.
Yeah, but I think that it's too fast. I mean, normally the tachyons that we are familiar with in string theory, they roll probably too fast for them to be an inflaton.
No.
I think Michael has a question.
Yeah, I would like to take the opportunity to have so many experts here to ask one question which relates to something that Yuji mentioned in his presentation, namely about the spurious poles and the Xi and eta conformal field theory. So usually, and in the prescription by Verlinde, it said you should insert one more Xi field in the correlators, and the reason is the zero mode of the Xi. However, the Xi is a dimension 0 field, and it always at each genus it has one zero mode, but the eta having dimension 1 has G0 modes at genus G, or naively at least you would expect this. So why is it that at each order in perturbation theory you should insert one more? I mean, there's also one Xi more than eta. There's also a paper right by Karo Watamura et al. Who say one should actually also include at G loop order G factors of eta. So what's the opinion of the experts about this? Maybe Nathan, you want to say something?
Yeah, I know this paper of Caro, etc. So I think their prescription is correct, and it's equivalent to the Verlinde prescription. The prescription is around every A cycle. So you have to decide which are the A cycles and B cycles. You integrate an eta ghost, and together you put a factor of delta of, you fix the picture going through that loop.
So how is it equivalent to the Verlinde prescription?
So the Verlinde prescription is essentially you define correlation functions such that the betas and gammas, the things of zero picture, don't have any spurious poles. But they don't get the prescription by doing a functional integral over the bosonized fields. They just find an answer which has the right properties. I think that's the way I understood their paper. Whereas the Caro paper, they tried to do an honest functional integral over the X's and etas. And they show that with this prescription, there's some hand waving, because the hand waving part is that they get the delta function. So when you integrate the etas around the cycles, it turns out you get the delta function from the picture tells you that only one point of this cycle contributes. That essentially instead of getting a contour integral around the etas, the delta function essentially fixes the positions of all these etas that you're integrating. But this delta function it's a funny delta function because it's a holomorphic delta function. So it's not the real delta function. So, I mean, it fixes it if you assume that, you can convert the holomorphic delta function into an actual delta function. But assuming that, then the answer they get is essentially the same. That and the spurious poles comes essentially when the etas happen to hit a Xi.
So are you saying that what Verlinde are using is kind of after integrating out these extra zero modes of eta already?
I think so. So I mean, they show that the two are equivalent. So it's not. I mean,
there's no contradiction.
Anybody else has any? Yeah, no, certainly there's no contradiction. I mean, essentially, Caro was trying to justify I think, trying to justify the Verlinde formula. I don't know if anybody has any other understanding of how the Verlindes got their formula.
Yeah, I think they just guessed. I mean, they had some certain set of consistency conditions, and then they just guessed that that's the correct formula.
Yeah.
That's my understanding.
Yeah. But I think this Carlo paper is correct. I mean, the only part that's, as I said, is hand waving is this holomorphic delta function. They have to assume that, that actually fixes the positions of the etas.
So one should understand the Verlinde formula is arising after integrating over the eta zero modes already. I mean, at least morally, that's what you are saying.
Yeah, I think what Verlinde would like to say, and I think, is that the betas and gammas are the well-defined objects. And the etas and x's are just some auxiliary thing that we introduced just to, to make some life simpler. But I think in some sense, you shouldn't try to do a functional integral over the etas and x's because they're not the actual variables. I think that's the way that probably what Verlinde would say.
Okay, thank you very much.
We are going a bit over time now, so we could, I think we could finish the panel discussion. I'd like to thank the panelists for starting, well, for leading the discussion, and then all the nice questions that came after. And it would be nice to take the picture now. So if everybody who wants to be in the picture could turn on the cameras, we'll do it. Harold, are you ready to do it?
Yeah, just 1 second. I will try to go full screen and then I will do it. So just stay with the camera until I say thanks. Thank you. I think it's good.
Okay, thank you. We'll start again in 10 minutes. So if any of the following speakers is around to try sharing the video, just as a test, it would be nice. I see that Alison and Alex are already there. Can you hear me, or are you away?
their presentation before.
So Alex is here, so he's just preparing. Alex.
Maybe Allison wants to try sharing first because it's she's the first speaker.
That's fine. Just a test, and I don't think she's here. I mean, she's
Okay.
logged in, but I don't hear her.
Okay, just a second.
Try also to move forward in order to avoid the issues.
Yeah.
Wait, I mean, she was here before.
No, she is here.
Oh, okay.
She's just not responding. I think she's probably away for the break.
Okay, I'll try sharing my screen.
Mhm.
Boom. Does this work for everyone?
Seems to be, or can you put it on presentation mode and move the slides a bit so we see it works? Okay, good. Seems it's working. Thanks,
Okay.
Alex.
No problem.
Hi, Alison. Do you want to try your screen sharing?
Hi, yes, sure. Can you see my screen?
Yeah, it's working. Presentation mode, and can you move the slides a bit?
Yes.
Okay, good.
Yes.
Thanks.
Mhm.
I see Saemann is here also. Harold, can you make him co-host? For the people arriving now, we are just 5 minutes late because the panel discussion took a bit longer than planned. Christian, are you there?
Yes, I'm here.
Yeah, would you like to try your screen sharing?
Yes, okay. At the moment, it's not particularly interesting. 1 second. Does this work?
I don't see.
Yeah.
1 second. Now it should work.
Yeah, I can see it. Can you put in presentation mode and move the slides a bit?
All right. Yes. Sorry. Let me share. 1 second. So how do I go back? Probably should share the. Just the window, right? It's better?
Yeah. Can you skip the slides? Yeah, okay. I'm just asking this because we had some problems before.
All right, yeah. Well, this should work.
Okay, thanks. I don't see Kasia there. Rejzner. Okay, but there is a break before her talk, so I think we can restart. Igor Pesando will be the chair for this second section.
Okay, thanks a lot for the nice conference, for the cozy conference, because it has the right styles to be able to talk with people. So let us start essentially the last session of this conference. The speaker is Alison Pinto, who is a PhD student at Humboldt University, and he or she will talk about gauge invariant perturbation theory via homotopy transfer. Please, I will remind you when you have 5 minutes left. You can start when you want.
Also, your mic is off.
Yeah, yes, okay. Okay, can everyone hear me?
Yes, we can.
Okay, great. Okay. So, yeah, thank you to the organizers for inviting me to give this talk today. I would like to share with you my joint work with my PhD advisor, Olaf Holm, and postdoc Christoph Chiappino. And my talk is going to be about gauge invariant perturbation theory via homotopy transfer. So first, I'd like to motivate why we are thinking about gauge invariant perturbation theory. And this is because we are after, one question that we are after in our group is, are there signatures of massive string modes in the cosmic microwave background? So in order to tackle this big question, we want to expand double field theory, weakly constrained double field theory, around time-dependent backgrounds and apply this to cosmology. And it turns out that this is not so easy. And this is because of the doubled nature of double field theory, which makes it difficult, for instance, to see which gauge fixing conditions we need in order to compute correlation functions. And on top of that, the space-time split adds complications. So we asked ourselves, what do the cosmologists do? And in cosmology, there is a procedure from Bardeen in the 1980s who decomposed metric fluctuations into scalar, vector, and tensor modes and built gauge invariant combinations of those in order to compute correlation functions. So when we try to apply this in double field theory, we ask ourselves, is there a systematic approach to this procedure? And can we extend this procedure to all orders in perturbations? Because we'd like to compute higher point correlation functions. So, so with that, I'd like to just give you a short outline. So first, I'd like to show you what I mean by gauge invariant variables and what they look like. And then going to just review L-infinity algebras and homotopy transfer, which will be important to describe our procedure that we found to write down gauge invariant variables to all orders, and then apply this to gravity on flat space and gravity on FLRW backgrounds. So I'd like to start off with Maxwell's theory, and I know that this is super simple, but I'd like to make sure that everyone's on the same page. So the goal here for us right now is to write Maxwell's theory in a manifestly gauge invariant form. And one way of doing this is to decompose the gauge field A mu into a scalar part and vector part. So, well, just first do the space-time split, so A0 and AI, and then split the vector field in terms of a gauge invariant part, A hat, plus the gradient of a scalar, psi. And now psi can be written in terms of the original AI via the invertibility of the Laplacian. And by reading off how these components transform, we can see that A hat, the divergenceless vector, is gauge invariant, and we can build a gauge invariant combination of A0 and psi, which I call here phi. And by inserting this decomposition into Maxwell's equations, we find two equations, which is that the Laplacian on phi is 0. And by the invertibility of the Laplacian, we have that phi equals 0. And then the second equation tells us that box on A hat is 0. So this is exactly what we expect, because we expect two physical degrees of freedom of the photon. And this is, we can already read this off at the level of the action once we reinsert our decomposition into the original action, and then reorganize the terms in terms of these gauge invariant variables. So this is super simple in Maxwell's theory, but you can imagine that for gravity and then for other theories that doing a decomposition and then reorganizing the terms can be quite complicated. So that's where homotopy transfer comes in. So just to briefly review what Olaf talked about on Monday and Tuesday. So an L-infinity algebra is a graded vector space with multilinear maps, which are graded symmetric, and they satisfy generalized Jacobi identities. And now the free theory is encoded in a chain complex, which is a sequence of vector spaces where the differential squares to 0. So for instance, for Maxwell's theory, for the gauge parameter lambda, we can map to a field named mu. And for the field A mu, we can map to its equation of motion, and for the equation of motion, we can map it to a Bianchi identity. And now, this is the free theory, but in order to describe interactions, we need to equip this chain complex with an L-infinity algebra. So to write down the gauge transformations to higher orders, we can write them by the L-infinity maps, which look like so, and then also for the equations of motion. And so now how does that help us write down our theory in terms of gauge invariant variables? Well, so the first step is homotopy transfer. So first we write down our chain complex for the free theory, and we can project down to a gauge invariant complex, which I call here X bar. And this P0 here is, I just want to stress that this P0 is really the projection from the free theory to the gauge invariant part. And so there's no L infinity algebra yet on the gauge invariant space. But what is also good to note here is that P0 and I0, the inclusion, are quasi-isomorphisms. So that means that the homologies of both chain complexes are isomorphic. And that's exactly what we want for the physics to stay the same. Now, the L infinity structure on X can be transferred to X bar if there exists some homotopy map, which means that I0 composed with P0 is the identity up to homotopy. So now that we have established that the gauge invariant chain complex also has an L infinity algebra, we want to know what this projection map is to all orders in perturbations. And for that, we want to use the homological perturbation lemma. Now, okay, so in order to set up the homological perturbation lemma, we start with homotopy equivalence data, which is basically just two quasi-isomorphic chain complexes, like we just saw on the previous slide. And the homological perturbation lemma tells us how to perturb this data. So if we suppose that B1 gets perturbed by delta, then the homological perturbation lemma says that if the perturbed maps, the inclusion and the projection, take this form, then the perturbed data is also a homotopy equivalence data. And for our case, we take delta to be nonlinear maps in our L infinity algebra. Now, and I'd like to stress that the HPL does not by itself ensure that the inclusion and the projection maps are L infinity morphisms, but the strong deformation retract is what is actually required for I and P to be L infinity morphisms. So once we have the strong deformation retract and homological perturbation lemma, which gives us a recipe for how to compute the perturbed projection, then we can start to apply this to our gauge theories. So in order to apply, so now that we know what the projector looks like, well, we can write down the gauge invariant variable to all orders. That's simple. Then how do we rewrite the action? Well, for this, we need to define a map, which is a sort of nonlinear extension of the inclusion map that looks like this. So here, phi of A generates infinitesimal gauge transformations. So this really is a finite gauge transformation of the gauge invariant variable A hat. So this just says that, well, A mu, the gauge variant field, is equal to the gauge invariant part, A hat, plus some pure gauge terms. So for instance, in Young-Mills, this is what it looks like to next order. And once we have this, all we have to do is replace our gauge field with the gauge invariant one plus pure gauge terms into the action, then all the pure gauge terms in the action will drop out because, of course, the action is gauge invariant. So, so in essence, you just perturb you just write down the higher order action, and then you replace everything with these hats and say, okay, this is my gauge invariant action. And now this is really not surprising because this is exactly what you do for gauge fixing. But what's interesting is that now we know how to write down gauge invariant variables to all orders, and we also have an algebraic procedure for this. So now I'd like to apply this to gravity on flat space and then gravity on FRW. So for gravity on flat space, we have this chain complex here. And where, and we first decompose the metric fluctuation h mu nu into scalar, vector, and tensor modes, just as in Bardeen's procedure. And these vector modes here are divergenceless, and the tensor mode is transverse and traceless. Okay. So now from those components, we can build gauge invariant combinations. And therefore, we can write down the projection from the space of fields to the space of gauge invariant ones. And here's what they look like. Then we can write down the original field, h mu nu, in terms of the projection plus their pure gauge terms. And the pure gauge term here, so a mu is in terms of these components of the metric that we saw before. And from this, we can infer what the homotopy map is. And we find that S on H equals just a mu. And that just then allows us to be able to reinsert to just put hats everywhere on our quadratic action, and obtain finally our linearized Einstein-Hilbert action in manifestly gauge invariant form. So here, this the first term of this line, this is exactly what we expect because the graviton has 2 degrees of freedom that propagate, and then the rest of these modes do not propagate. And for instance, the scalar modes can be reorganized in a way that is diagonal like this. So now moving on to gravity on FRW backgrounds. So the starting point here is the Einstein-Hilbert action with a minimally coupled scalar field. And we expand in around FRW, so and work in conformal coordinates. And chi here is the scalar field, where chi 0 is the background, which is only dependent on time. And well, if you naively just expand this action around quadratic to quadratic order, then you get this really long, messy thing. So that's just to show that, well, if you do the decomposition and then try to reorganize this action in terms of gauge invariant variables, it's actually quite nasty. So instead of going there, we write down the chain complex and write down the chain complex. And it's easy to write down our gauge invariant variables, just as we did before, except now we have an additional gauge invariant scalar theta because of the fluctuation of the scalar field. And again, these are what our projected fields look like. Sorry, it's kind of weird. Right, okay. Sorry about this. Okay, so then, so once we've done that, we can write the fields as their projections plus pure gauge terms again, find the homotopy maps, and we find that the homotopy is just equal to A mu, just as before in the flat space case. And now, finally, we arrive at the gauge invariant Einstein-Hilbert action, expanded quadratic order around FLRW. So this is already much simpler than what we had before. However, we have to simplify the action of the scalar modes, and this is supposed to be the Mukhanov-Sasaki action. So in order to simplify this, we still need to take into account the constraints, or we can use some field redefinitions that are quite complicated. But in any case, once you solve for the constraints, then indeed you arrive at the Mukhanov-Sasaki action, where the Mukhanov variable is just A theta plus Z psi, where Z is this background quantity. And finally, in order to write down the gauge invariant action to cubic order, we need to use the perturbation lemma. And this is what the formulas look like for that. Now, I didn't write explicitly what this is in terms of our components, but at any rate, so this 2 bracket is just the Lie derivative, because S of varphi and H belongs to the space of gauge parameters. So this is just the Lie derivative of 1 plus I0 P0 H mu nu with respect to A, which is just the homotopy. And when you work this out, it's actually quite long. So I didn't write it here. But at any rate, you can still, once you have the cubic action, we just insert, we know that this is the gauge invariant variable to cubic order.
5 minutes left.
Yeah, I'm just about to conclude. So in conclusion, we have been able to find a method to write down gauge invariant variables to all orders and perturbations, and an easier way to arrive at a manifestly gauge invariant action. And this is going to be important to compute correlation functions for cosmology in particular. And some open questions would be how to apply this algebraic framework to compute endpoint functions in a manifestly gauge invariant way. And another question is, can one use homotopy transfer to solve for the constraints? So as we saw before, even though we have a gauge invariant action, we still don't have it in a diagonal form or in a nice way, a nice form that we can use to compute correlation functions. So it would be nice to be able to use homotopy transfer for that. And then last but not least, we'd like to apply this to cosmological double field theory. And for this, Olaf and I have a paper coming up, hopefully by the end of this year. So yeah, that's all for today. And thank you so much for your attention.
Okay. Okay. Thanks a lot for the seminar. Is there any question? not, I have one. I'm not sure I have understood everything completely, but in the simplest example of a Maxwell theory, it looked like that you needed a kind of gauge fixing condition. Is it true for all the other cases that you need a gauge fixing condition? And how does your result depend on the gauge fixing condition?
So you're saying, so you're asking, how does the result depend on the gauge fixing condition?
Yes.
You mean the final action?
Yes, the definition of gauge invariant fields.
No, so yeah, so well, the physics should definitely not depend on the gauge fixing conditions, and this is
true, but technically it doesn't seem so.
Right. Well, no, you can always arrive at a different gauge fixing condition from one gauge fixing from one. So it shouldn't really depend on what condition you use. And for instance, in the cosmological case, so our derivation of the Mukhanov-Sasaki action, for instance, was very different from how Mukhanov how they derived it. But still, we are able to get there, and because it's really invariant of what condition you use, it's a matter of field redefinitions until you arrive at the same result, I believe.
Okay, thanks. Because I was thinking, for example, to gauge theories, when you choose the unitary gauge, or you take something like Yang-Mills or simple QED with a scalar, and then you choose the unitary gauge, then what you get is somewhat different depending on the gauge. Also because the unitary gauge can have singularities which have a physical meaning. So this was my curiosity on the dependence of the gauge fixing. Okay, in any case, thanks a lot. Any other question? If not, thanks. Okay.
I actually raised my hand. Okay. Hello.
Yes, please.
Yeah. Maybe this was explained in Olaf's. First of all, thank you for the nice talk. Maybe this was explained in Olaf's talk. I don't remember quite. So is the point that once we use this homotopy transfer to write everything in terms of the gauge invariant variables, all the terms should satisfy this L infinity constraints? Is that kind of the point? It's why we want this way to write the action?
Sorry, all the terms should satisfy what exactly? What did you
like the L infinity constraints he described? Like for the scalar theory, he showed that the interaction terms, they follow the L infinity constraints. Let's say in the theory where you had no
the A infinity. I'm not sure what you mean.
L infinity constraints.
Yes, exactly. So yes, so the theory that you end up with also has an L infinity algebra.
So that is kind of our goal. That's why we want to do this homotopy transfer to write everything.
Yes, exactly.
Okay. Thank
you. Okay, thanks a lot. Any other question? No. In that case, we thanks Alison again, and we can move on to the next speaker. The next speaker is Alex Arvanitakis, and just to introduce him, he has got his PhD in Cambridge and been postdoc and he is postdoc, has been postdoc in Imperial College, and he is postdoc at the Vrije Universiteit in Bruxelles. So please, can you share your screen, Alex?
Yes. Okay. Can you see everything?
Yes, thanks.
Okay, shall I go?
Okay.
Right. Well, thanks for the kind introduction and the invitation to speak. I'm going to talk about some work with Chris Hall, Olaf Holm, and Victor Lecque, as it happens on homotopy transfer and also on double field theory. So lots of similarities to the previous talk. So the main concern of this talk is the following. Consider string theory, closed string theory on a Minkowski background. You know, you calculate string amplitudes and out comes the Einstein action coupled to the B field and the dilaton, or at least that is the action whose scattering amplitudes at 3 levels reproduce string scattering amplitudes of the associated string states. So we know, this is how we know string theory is closed string theory is a theory of gravity. But the question we're interested in is, can we find any fundamentally stringy features of this theory? And in particular, if you have a torus background, then you know, and I will review very shortly, that the fields, the metric and all the other fields, basically depend not just on the coordinates along the torus x, but also the coordinates on the T-dual torus x tilde, and this corresponds to the presence of momentum and winding, because we're talking about closed strings. So in 2009, Bartens, Wiebach, and Chris Hall constructed part of the effective theory of closed strings on a spacetime with a torus factor. And they did it up to cubic order, and they found that spacetime is indeed doubled in this way. And no progress has really been made since. So the question is, does double spacetime survive beyond cubic order? Or can we construct this double field theory beyond cubic order? Even to quartic order, there has not been any progress. So I'm going to outline how you can use, again, homotopy transfer to produce an algorithm for the quartic and higher DFT vertices, which basically takes the homotopy algebra of closed string field theory, which is an L-infinity algebra, and gives as an output the vertices of the effective, quote unquote, field theory of the modes we're interested in. These are the modes which are massless or would be massless in an uncompactifying background. And the nice thing about this procedure is it is manifestly doubled. You keep momentum and winding at the same time. It's consistent with gauge invariance. Whereas, for example, for those of you who have heard of this, if you've seen a strongly constrained double field theory, which is what you get if you forget about, say, forget about the windings or the momenta, but in an ODD covariant way, that is known to all orders. It's in fact even background independent, but it's not doubled because you don't have the momenta and windings simultaneously. And you can view this as a nice implementation of a proposal by Ashoke Sen for possibly non-Wilsonian effective actions, which this is, and I will outline why in a second. There are still some technical issues, so this is towards double spacetime, one would say. Okay, so let's see why spacetime is doubled. So as we know, if we have closed strings, we have two sets of oscillators, alpha and alpha bar. On flat spacetime, or indeed in any flat direction, the string can't wind. So the zero modes, just become, they agree, they give the center of mass momentum. Whereas if you have a torus, the zero modes remain independent. And one linear combination gives the momentum and the other linear combination gives the winding. And all of the string states, in principle, depend on both momentum and winding, certainly off shell. And on shell, I will outline how this dependence is constrained. For example, at level n equals n bar equals 1, where level basically counts the number of oscillators you use to build your string state, you clearly have simultaneous dependence on momentum and windings. So at these levels, these are the states that would be massless for an uncompactified background. Right, so these states see the double torus because we have momentum and windings. And because T-duality swaps momenta for windings, the two theories are equivalent. If we have original positions, then we should introduce dual positions and take them as seriously as we did the first ones. So we're naturally led this double point of view. So what Halves and Frw did is truncate the bosonic closed string field theory to the levels n equals n bar equals 1 to cubic order. And they also found that this theory is perfectly consistent, gauge invariant and everything. This is actually quite interesting because, well, this is not a Wilsonian effective field theory. Sorry about that. I'm in a balcony. In any sense, if you just if you calculate the mass of string states at this level, for example, even if you take an original torus of small radius, the states which have momentum excitations, they will be very light. Fine, we're happy with that. The states which have winding excitation, they will be really heavy. If you want to keep both sets of states, you really, you're not doing any kind of Wilsonian effective field theory. And the remarkable part of this action is not just that it's the truncation is consistent, it is also that this truncation is also local on doubled space-time. And the action for the effective modes is very similar to what you would get for if you expand an Einstein-Hilbert action around flat background. So you have a field EIJ, which is not necessarily symmetric, which is a kind of doubled graviton, and a dilaton field. And it has this lovely form. And everything, the interesting thing here, the stringing component, or the stringing weirdness, if you want, is that the level matching condition from string field theory means that everything obeys this condition, this quadratic condition involving derivatives. It's a kind of Laplacian and double space-time. Right, so the fields and the gauge parameters obey this level matching. And moreover, the gauge transformations you get from string field theory, they descend to double diffeomorphisms of some kind. Of a sort, you know, notwithstanding the level matching. Okay, so we could take this action and we could consider the problem of constructing, for example, the theory to quarter-quarter using a Noether method. Well, actually, you have a bit of a problem. And this is why it hasn't been done, or it hasn't appeared in the literature. Lots of people have tried this privately, including myself. For example, because of this level matching condition, every time you write a term, you need to introduce projectors to the zero locus of this in every possible permutation. So you get a bit of a combinatorial explosion in your quartic terms. And this doesn't happen at cubic order basically because of momentum conservation and when you have three momenta coming in. And the other reason why this construction is difficult is that in general, we expect you will have so-called co-cycle signs. And these are sign factors that depend on momenta and windings that appear in the string field theory of the torus relative to string field theory on flat spacetime, and were found long ago to be relevant for gauge invariance at quarter-quarter, and also for the symmetry of the string vertices, if I remember correctly. So, so you have even more of a combinatorial problem, of course, if you take both of these things into account. What we're doing instead is use a method that doesn't suffer from these properties. You sort of, both of these things are taken care of on the string field side, and we use machinery that preserves, you know, the the level matching or weak section condition, and whatever co-cycle sign should they be present. You know, they're in principle, they're implicitly there in the string field side, so we don't have to guess them. They're just carried along for the ride. Okay, so I think we just heard an L-infinity talk, so I don't have to spend too much time explaining this, but basically an L-infinity algebra is a chain complex with a differential d that squares to 0, and it has a collection of brackets, including a binary bracket, which would be a Lie bracket, except for a contribution involving the differential, and a cubic bracket. You get Jacobi identities for all of these things, and they all talk to each other. And there's a general dictionary, if you want, between the maps L-infinity algebras to field theories, which was articulated by Barton and Olaf a few years ago. And this is, disregard the second blue note, that is a typo. Basically the vector space where the L-infinity algebra lives is built out of the space of fields, gauge parameters, equations of motion, and so on and so forth. If you thought about the BV formalism, you get a lot of the same things, but I should say that in the BV formalism, you always have some kind of anti-bracket which is non-degenerate, whereas here you don't necessarily have an anti-bracket. In fact, a lot of the examples in this paper, they cannot admit a non-degenerate inner product by accounting reasons. And the original canonical example of this was, of course, the covariant bosonic tree-level closed string field theory of Barton, where the differential I mentioned is just the worldsheet BRC differential. There exists some connection of vertices, which I'm not going to have to discuss explicitly in this talk. And the inner product, which I will discuss very explicitly shortly, is the BPZ inner product with a ghost insertion. And then the basic claim is you take the BC ghost system, and then you add, and then for any matter CFT, you can construct a collection of higher brackets, higher string vertices that make the entire thing into an L-infinity algebra. This is generally like you know, an honest an L-infinity algebra. So there's no simplifications. For example, it's the bracket B3 of 3 arguments corresponding to the quartic vertex was non-zero. It would be a differential graded Lie algebra, but this seems not to be the case. Although there do exist equivalent formulations, so non-covariant ones, for example, the Kyoto group theory, which apparently can be cubic. And in this case, instead of an L-infinity algebra, you have a special case of that, which is a differential graded Lie algebra. So this, I assume, is reasonably familiar, so I'm skipping. So this last fact I mentioned, the equivalence of, you know, some L-infinity monstrosity with brackets of all arities versus the cubic light cone-ish string field theory of the Kyoto group. How can these things describe the same physics? And the answer is that the notion of equivalence of these L-infinity algebras is actually more wide-ranging than for Lie algebras. You have a notion of homotopy equivalence, which includes maps which are not invertible. And basically, this is some tower of linear maps from one vector space to the other, and they're multilinear. And the critical point is that the linear map this phi1 preserves the cohomologies under the D bracket. There's lots of compatibility conditions such that this preservation of cohomology makes sense. And this is a nice and physical requirement because you can identify the cohomology in terms of scattering states, both in string field theory and in general field theories. And then homotopic transfer is just a machine that lets you take an L-infinity algebra on vector space X and a phi1 which preserves cohomologies and transport it into another chain complex Y, such that the algebra on Y is equivalent to the original one. And this is a very nice algorithm. For example, if this new space Y is a subspace, then the input includes this homotopy map, which is a linear map on the original vector space, satisfying this homotopy identity. This is involved with the anti-commutator between the differential. For us, it's the Worldsheet BRST differential and the homotopy map. And the critical point for us, because, well, I don't have a powerful string field background personally, is that the conditions for this homotopy transfer only involve the differential, the homotopy, and the projector. These are things which appear in the free theory. The D is the Worldsheet BRST differential, so you can check it in string theory rather than string field theory. And then how do we construct these homotopy things? Well, one observation which was made by these other people I mentioned a few slides ago is that the construction in the nice paper by Sen on effective string field theories, that naturally gives an ansatz for the homotopy. It's basically a propagator including a projector yielding only the states which are to be integrated out, as it were. Now, the status of whether this is an honest integrating out or not depends on whether the homotopy plays nice with the inner product and so on. I'm not going to bore you with the details that way. But if you want to assume to make a few more assumptions, you can view this as some kind of tree-level Feynman diagram expansion with states to be integrated out appearing in intermediate propagators. So how does this apply to our problem? Well, as I said before, to do this homotopy transfer, you need a map phi1 that preserves the cohomologies, and say phi1 is the projector into the subcomplex of the state you want to keep. So the question is, we want the states of levels n equals n bar equals 1. Can we find a homotopy that works? Actually, the answer is no. But you can take a projector of states at levels 1 and the state at level 0, which is the tachyon. It just works. It's a nice fact about the string spectrum. You can calculate it if you don't believe me. And this gives a construction of the vertices and gauge transformations of some honestly double theory of, the DFT double field theory we actually want, plus some tachyon field, and the two things interact with each other. And we checked that this agrees with the result of 2009, up to elimination of auxiliaries, which is also an instance of homotopic transfer. Okay, so this is a special case of very general construction. So given a starting L-infinity algebra, we get an effective L-infinity algebra. But the question is, did we originally start with an L-infinity algebra? So we checked this quite carefully, and we found some subtleties involving the inner product, the BBZ inner product on the closed string side for the torus background. So now I'm going to outline how this, what this subtlety is. So if you look at vertex operators on the torus, then you might have seen, or at least be vaguely familiar with the fact that you take your naive tachyon vertex operators, where these k and k bar depend on the momentum windings. And so these operators just aren't bosons. Like, you calculate the commutation relation, you shift, it's an equal time commutation relation where you use radial quantization, and you get this sign factor, this -1. And this is a bit of a problem, well, depending on what you want to do. And a fix for this is to introduce an operator, a co-cycle operator, which depends on the momentum windings and also depends on the oscillator zero modes. So this is an example of a thing that works. In fact, there's a moduli space of choices, if you will, which could possibly work. And what I'm about to say is going to work for any of them. And so here's the paradox you get when you consider these things. Say you consider the state operator correspondence. You want to see which ket is created by the original vertex operator and the corrected one with a co-cycle operator insertion.
5 minutes.
Sorry?
Left.
Hello?
5 minutes left to the
Ah, okay, very good. So you take, so because these are oscillator zero modes, they just annihilate the SL2Z vacuum. So the original operator and the corrected one create the same ket, right? This should be obvious. You don't even need to do a calculation. But they create different bra states. So this is easy to see if you look at the corrected one. So the point is, when you move the co-cycle past the vertex operator to the left, the two things don't commute. They commute up to a sign, and the sign just appears here. And this sign is -1, at least for the co-cycle operators. I checked for the states with the product of momenta and windings equal to 1, modulo 2. So this enters the reflector states of string field theory. And it also enters the inner product in the L infinity output, which was why we were initially concerned with this point. So you seem to have an ambiguity in the reflector states. But there is actually a simple resolution, at least for the free theory. And the resolution is the following. So you consider the inversion map, and you demand that this is actually realized through the transposition associated to the BPZ inner product. Now, as far as the oscillators are concerned, the transpose is known because dx is a conformed primary, fine. But the position zero modes, the transformation is not fixed. But you can fix them. You can fix them by demanding that the, say, corrected tacking vertex operator is a primary under this global conformal transformation. And this is a non-trivial point. You do that, it's a simple calculation, but then you find the co-cycle operator in the transposition formula. Therefore, you pick some co-cycle operator that fixes your commutation relations, and then this corrected tacking vertex operator is a conformal primary, and all of the other ones aren't, because you get the wrong transposition formula. You picked some other kind of co-cycle operator, or if you didn't pick any one at all. And if you actually do that, then you get the reflector that was obtained long ago when the Kyoto group and Kugo and Tsuiba were studying T-duality as realized in closed string field theory. So that was a nice sanity check for us. Okay, and I conclude my talk now. Hopefully I'm not out of time. So I outlined a scheme where one can in principle obtain the vertices of this double field theory. Of course, you have the tachyon, which is probably most likely eliminated if you started with this whole procedure, but from superstring field theory, which was introduced quite recently, and with an L infinity algebra structure. And what might be more interesting for this crowd is this puzzle involving the co-cycle operators and minus signs of the torus CFT. So we seem to have resolved this in a way that selects exactly one choice of corrected vertex operators. And the natural conjecture is that this is exactly what you need to resolve the co-cycle sign issue. Sorry about that. For the higher brackets and vertices, if you calculate them correctly for the torus CFT relative to that for an uncompactified background. background. So I think I ran out of time. Thank you.
Thanks a lot. No, you had still 1 minute and a half. So thanks a lot for being so sharp. So is there any question? Okay, there is a question, there are two questions. The first one by Yuji. So please, Yuji.
Hi, could you come back to the 2 times 10 to the 6 data question?
Yes.
So I thought so you're saying that you are not able to project onto the only massless states, and you also need to project onto the massless plus tachyonic states. Is that what you're saying? Why is that?
That is because you want to satisfy this relation, the one that's in the box.
So I thought the condition on the P is just commute with the VLST operator, and I think it satisfies for the projection to the massless state.
Yeah, so this is a condition simultaneously on the projector, so the states you want to keep, and on the homotopy. And it also implies facts about the homology of the BRST operator on the projected subspace. So it needs to be the same as the original one. Right, and this is just a brute fact about the BRST homology for generic torus moduli in Euclidean signature.
So there's a, okay, I don't see any problem. So
that was a little, wasn't the original argument of Sen that the truncation to the massless sector was completely consistent?
Yes, indeed.
So what was wrong with the argument, or?
Well, I think probably the right way to view it is, so homotopy transfer can only do so much for you. So it may be possible that there is a might be a smaller theory, which is what Sen argued for, which is perfectly consistent, and then there is an L-infinity morphism, which is not an equivalence, it's an injection. So this is a kind of consistent truncation in the supergravity sense. You need to do more physics to deduce that, but we decided to use the machine that does lots of work for us, and it doesn't involve thorny questions of truncations and so on.
Okay, so so physically it may not be a good idea to integrate tachyon to get a low energy theory, but then mathematically I don't see any problem. So and classically you can integrate out tachyon. So that's why I was a little bit confused. Thank you.
Okay,
fair enough.
Thanks. There is still another question by Dimitris, please.
Hi, Alex. Thanks for a very nice talk. So this co-cycle factor, so the P and the W are the momentum unwinding of two different vertex operators, right? They're not of the same vertex operator. Is that correct?
Which co-cycle are you referring to?
So e to the I p I, sorry, pi I p W primed. The one in the last slide, for example.
The one in the last slide. Yes. So I think
the P and W primed. So the prime denotes a different vertex operator to the P one, right? So the different.
Yeah. Hence the prime. So
yeah.
So what happens then is you have, say, a quartic vertex, and then for every two states, for example, you have a P of one state, a W of another state. You have some sum of the things.
Yeah.
Sorry,
so my question.
Yeah.
Sorry, my question is so actually there's some work that I did with Ed Copeland and Paul Safin a few years ago, where we were finding some vertex operators that seemingly had negative norm, but of course there was no reason for them to have negative norm in toroidal backgrounds, in general toroidal backgrounds. And by thinking about these conformal maps, and we realized that actually there's a the Euclidean adjoint of a vertex operator should have an additional phase, which is an addition to the cocycle that you note, which is basically minus to the PW, whereas both P and W are the P's and W's of the same vertex operator. The one is taking the Euclidean adjoint of. And if one doesn't include this, then the OP of a vertex operator with its Euclidean adjoint comes out negative, which would seem as if it has a. There are some examples like of vertex operators, where you can just compute it and see explicitly that it comes out negative. And these signs are and these additional signs are needed. And we proved that actually for the complete set of states in string theory, all of them.
Oh, that's
we
interesting.
computed
So
these two functions explicitly.
maybe we should see. Maybe we should see whether this is consistent with this proposal, because I'd like to think
Yes.
you know, we worked out the
Yes.
BPZ thing, and that's the only thing it could be. But maybe.
Yes, it's very interesting.
Actually, yeah. So you see here, if
Yeah.
you move the cocycle past the vertex operator to the left, you will pick up a sign with P and W on the same state, like you said exactly.
Okay. Yes. Those are of the So V. So now
It was the argument here. Yeah. So here I move it right to left, and you pick up a sign, which I censored. Its explicit form, but it resolves to this. I think this is in the paper fairly explicit.
Very good. Yes, that looks like it might be what I'm referring to actually. So P and W here are on the same state, or is that a different state? The PW that equals 1 mod 2.
This is the same state.
Okay, very good. That's interesting. So it looks like it's this. Okay, very good. So that might be the same phase then, right? I think, right? Is that correct? I mean, I don't know.
It looks the same, but I
anyway, we
haven't,
can talk more.
I was not familiar with your paper, so we'd have to chat more.
Actually, a lot of this is unpublished. We were going to write a note up on this, and I mean, we stated, I think, in a footnote of our paper this conclusion, but we didn't write up the reasoning. I mean, it's somewhere, some draft of paper somewhere hidden away in some folder. So
Okay.
Yes,
yeah.
No, thanks.
Okay.
For
Thank you.
the questions. It's time to move on to the next speaker. So we thanks again Alex for the interesting talk, and we move to Christian Saemann. And just to introduce him.
Yeah, I'm here.
He was a postdoc at Trinity and the Heriot-Water University, where he is now permanent. So please, Christian.
So first of all, let me thank you for the invitation to give a presentation here. I wished I could have attended more of the conference. There were very interesting talks. Unfortunately, I had lots of teaching. We just had semester starting. After we've heard already quite a bit about L-infinity algebras and applications within the BV formalism and field theories, I thought I could probably push a little bit the homotopy algebraic part of the conference further and show a little bit more about the background, how to generalize these things, in particular present a generalization that has very important applications to physics. I should mention that this is work with my postdoc Laren Boston and PhD student Yonro Kim, and with my former PhD student Leonard Schmidt. Okay, so the question that are motivating this work is, first of all, a search for algebraic structure underlying the Courant algebroids. You know that they are very important in the context of generalized geometry and double field theory. And the other big question that I want to focus on are what are good curvatures for non-abelian gauge potentials like the Kaplan two-form field that we have in string theory. There are a couple of other questions that are also motivating this work, but let me not stress them here. They're more mathematical and not directly related to string theory. Okay, so what's the first question is the algebraic structure underlying Courant algebroids. So there are, of course, already quite a few answers in the literature, and the most impressive, most important is probably by Reutenberg. So he stated simply that an exact Courant algebroid is simply a symplectic DG manifold. So you have a symplectic structure on a graded manifold, and you have a differential. And if the symplectic structure is of a particular degree, then you encode a Courant algebroid. The explicit picture is given here. You have your manifold. You have your tangent bundle, but you shift it in degree by 1. And then you take the cotangent bundle of that, shift the degree by 2. because it's a cotangent bundle, it comes with a natural symplectic form, right? So this is canonically defined. And the symplectic form introduces for you a Poisson bracket. On that manifold, you have kind of like a Hamiltonian that you can define also. I mean, this part is canonical. This is a twist that you can introduce for Courant algebroids. And then you have, with the usual construction as a derived bracket, you have a differential, as you know from the BB formalism, right? And that extends, of course, to symplectic DG manifolds. And this is how you can describe very elegantly the Courant algebroid. And this in particular contains all the Courant bracket, the Dorfman bracket, as you usually know. Right, so in particular, the Dorfman bracket can be described like this, and the Courant bracket can be described in this fashion. So these brackets are particular cases of two structures. First of all, the Courant bracket is a part of an L-infinity algebra, and this is quite naturally actually from this perspective, because you define differential graded commutative algebra, and that's dual in a particular sense that I'll explain to an L-infinity algebra, and this has been known for quite a while. On the other hand, this is part of a DG Leibniz algebra, and Rogers pointed that out in 2011. However, here there's a slight mismatch, right? I mean, DG Leibniz is just an ordinary Leibniz algebra, where L-infinity algebra has more categorical flavor to it. And so you can ask, okay, is there a little bit more that we should do here to get the DG Leibniz structure under control? So it might seem a little bit like a niche question, but as you know, Courant algebroids underlie Hitchin's generalized geometry, so they're very important in supergravity to describe the generalized tangent bundle, which encodes the gauge transformations for Nabelian gerbe, which is after all what the geometric structure is that underlies the B field. And in fact, all the generalized tangent bundles that you know from supergravity, perhaps, they are all symplectic L-infinity algebras, and you can all define them in this language in a very nice way. So understanding these algebraic structures is, of course, very important. Dorfman structures, on the other hand, are very relevant in the context of tensor hierarchies. So if you want to define gauge theories that use these generalized tangent bundles, and they're, of course, very currently relevant in double and exceptional field theories. So in order to understand the above, it's certainly useful to have a better grasp on what the symplectic L-infinity algebras are that you construct from these generalized tangent bundles. Okay, so that's the first question. The question that originally motivated the work more for me is I'm interested in trying to construct higher non-abelian gauge potentials and to construct good curvatures in the presence of a B field. And there's actually already an answer in the literature for the Quatre-Mont field, and has been around for a long time and originates from the context of heterotic supergravity. So you see these things are really, really old, right? So we know that we have an ordinary two-form curvature for one-form potential. And now if we want to couple this consistently to a two-form potential, we take the curvature, but we better include the Chern-Simons term, or rather the Chern-Simons 3 form, of that particular non-abelian gauge potential that we have around, right? So this is a little bit at odds with what you get from the usual literature on non-abelian gerbes. So there's mathematical literature that describes non-abelian gerbes or non-abelian generalizations of principal fiber bundles to categorified groups. So these are exactly the generalizations that you would expect mathematically to describe these. Because if you look at these from all kinds of perspectives, doesn't matter how you approach them, essentially you end up with these curvature forms, right? So F curvature is fine, that's matching, but the H curvature you see has a slight discrepancy. So instead of the Chern-Simons form, we actually have just minus the cubic part, and this ADA term is actually missing, right? So this is what you find if you dig a little bit deeper in the literature. And this is actually at the heart of the problem why many people think that non-abelian gerbes are useless and they don't bring anything new to the table, and we shouldn't look at them in the context of the 2-0 theory or so on. So that's essentially the crux of this underappreciation in the sense of non-abelian gerbes. And then Hisham Satie and Urs Schreiber, they clarified the geometry of this particular case, certainly, or the algebra, I should say. So how you modify the curvatures and why you do that, or rather they said how you modify the curvatures, certainly, namely what you have to add. You have to add this AF term in order to complete the picture. And if you combine AF minus this one, you get precisely the Chern-Simons forms, right? So you have to adjust these curvatures. And this is a general story in the context of non-abelian gerbes. You can't take the ones that you find directly in the literature, but all of them need an adjustment, okay? But now the big question is, where does this thing actually come from, right? So this is not part of our high gauge algebra structure. So if you look at the L-infinity algebra that underlies that, and I'll go in a little bit more detail later, excuse me, then you see that this structure is not in the algebra. So you can ask, okay, where does this actually come from? Here it's rather simple because it's just a killing form of the Lie algebra that you have here, in which A takes values. But in more complicated cases, more complicated generalized tangent bundles, you would also like to have a good understanding of where this thing actually comes from, where these adjustments come from, right? Okay, relevance of third questions is we would like to have higher principal bundles with connections in gauge supergravities and so on. They're certainly there. And if you want to do something global, unless you do it in the right mathematical framework, you're certainly risking to get inconsistency. So that's a good idea. Heterotic supergravity, tensor hierarchies. And also, if you would like to describe six-dimensional superconformal field theories, like 1-0 theories, 2 zeros might be a little bit hard, but 1-0 theories you can do. You should use higher principal bundles to make sure that everything is mathematically consistent, at least, right? From mathematics perspective, is that higher geometry would be much less beautiful if we didn't have these in a sensible way. Okay, so what we found is essentially that all these 5 questions, in particular the first one and the third one that I asked here, have a very simple unifying answer, and the answer is just simply L-infinity algebras. So a generalization of L-infinity algebras. And I would like to introduce them and then show you quickly how these solve the problem. Okay, so we started our research with a few initial observations. So first of all, within generalized geometry, it's not too hard to see that the Dorfman bracket is actually part of what's called in the literature a hemistrict Lie-2 algebra. So that's a particular categorification of a Lie-2 algebra that is kind of orthogonal to L-infinity algebras, which would be, well, where you would have semi-strict Lie-2 algebras as a special case. But you have these hemistrict Lie-2 algebras. In addition, if you couple the B field to non-abelian gauge potential, this additional algebraic structure that I pointed out can be regarded as the alternator of a general weak Lie-2 algebra that has been discussed previously in the literature, right? So there are indications of the seeds of what you should actually do are already there and have been discussed to a certain extent, right? So in gauge supergravity, for example, you can show that the embedding tensor yields on the nose actually a weak Lie-2 algebra, right? There's precisely the structure that it encodes by a particular construction that we'll come to later, right? So we have all the hints that we want some weaker form of categorified Lie algebra that generalizes L-infinity algebras. And if you then look up the mathematics literature on this, and Reutenberg has already done the two-term L-infinity algebras in 2007. And then a PhD student from Göttingen extended that to weakly 3 algebras or 3-term L-infinity algebras in 2017, right? So these were constructions that went, Reutenberg was brute force categorical stuff, and Dehling was resolutions of certain operats. And now the question is, can we do something more general? Can we do the full infinity term L-infinity algebras, right? So the conclusions are we are looking for weak generalization of L-infinity algebras, and we want to generalize 2 and 3 terms L-infinity algebras in the literature. Okay, so the key ingredients in the story are operats and causal duality, and operats are certainly very good to have at your disposal when you talk about algebras, L-infinity algebras, and whatever, and causal duality is then the tool that allows you to go to the homotopy algebras. We won't need very much, and just an intuitive understanding is that operats are useful frameworks for describing algebras and their relations. And you have, we deal here with symmetric operats, and abstractly, you have some abstract operations with n inputs and 1 output, right? So this should be very familiar if you compare these to the L-infinity algebras that we've seen before. And then there's a composition prescription, essentially equalities between trees. So if you plug them into each other, then there are certain relations that appear. And these determine which operat you're dealing with. Is it Lie associative operat, L-infinity operat, or something else, right? So these are essentially these, the composition prescriptions are like the homotopy Jacobi identities that you saw in L-infinity algebras. Yeah, then there's additional technicalities, but for each operat, you can then define an algebra of an operat. And this is just then given by multilinear maps on particular vector spaces, or of course you can extend it to modules over particular rings. And the standard examples are the Lie algebra operat, associative algebra operat, commutative algebra operats, right? And then there's also Leibniz algebra. Now for each operat, you can, in a very natural way, define an infinity algebra by just giving the causal resolution of the causal dual cooperat, right? Whatever these scary words mean, I'll show you something very, very simple, namely how to get from commutative algebras to L-infinity algebras. And for this, recall that the Chevalier-Eilenberg algebra of a Lie algebra is just a graded vector space up here. And what we do is we shift it in degree 1, and we take the dual, and then we have coordinates function on this thing. And these are of degree 1, okay? And then we want just a vector field of degree 1 on this particular space. So if they are of degree 1, well, the vector field needs to have a differential, the derivative with respect to these coordinate functions. That is of degree -1, then I have to multiply with 2 of these coordinate functions to have something that's of total degree 1. I put some structure constant in front of it and a coefficient sign for convenience. And then it's not surprising, but these here, of course, the structure constant of my Lie algebra. And I impose the condition q squared equals 0. And this amounts precisely to the Jacobi identity on Lie algebra. Right? And now if I want L infinity algebras, of course, what I do is I just, instead of having here just coordinates of degree 1, I allow for different coordinates, and this will allow me here to have more polynomials, not just quadratic polynomials, but also linear terms, quadratic, cubic, and so on. And the structure constants then, of course, will give rise to all kinds of higher products. And then the condition q squared equals 0 is again the homotopy Jacobi identity, right? So that's a very straightforward way. So from the operatic perspective, what we just did is we did something very fancy, namely we considered the Lie operad. We took its causal dual, which is the commutative operad, and we then considered 3 differential commutative algebras over this operad, also well, commutative algebras, right? And then the differential on these algebras, on these 3 algebras, encodes the higher operations, right? Just as we saw here. You see here the differential encoded the Lie bracket. If we took higher differentials, we get all these higher brackets. And this is a general feature, right? So whenever you have an operad, you can take its causal dual. For example, you can take the associative operad, you can take the dual, which happens to be, again, the associative operad. And then you can take the free algebra over this with a differential, you get A infinity algebras, right? Then you can take the Leibniz causal dual operad, which is called the Schnabl operad, and similarly, you get homotopy Leibniz algebras. And this way you can construct homotopy algebras for any operad that you want, right? So that's straightforward in principle. And now the question is, of course, which operad produces the weak L infinity, EL infinity algebras? And there you just look what is known about the Lie2 algebra case, right? So the Lie2 algebra case, we have 2 operations. We have a binary operation of degree 0. And the new feature now really in the L infinity case is that we also have operations that are really a little bit stranger. So we have an alternator that's of degree -1. And it's still a binary operation, right? In L infinity algebra, if the degree is proportional to the arity, but here we have different operators of the same arity, but of different degree, right? And then it's rather clear if you think a little bit about it, how to generalize this. Namely, you have in general H-Lie algebras, you have a differential, and then you have binary operators of arbitrary degree such that they satisfy these relations here. They look a little bit complicated, but they are rather straightforward to derive. So the differential is clear. The differential should be derivation. That's clear. And then you have here a graded extension of the Leibniz identity, right? And then you have 2 other identities, and they are necessary to guarantee that actually this is compatible all with the differential, right? So you can define this in a rather straightforward way. So we got H-Lie algebras, and of course these now encode an operad. You can define the operad for it, and you can then take the causal dual. If you do this, you get an operad that we called IL, following the standard joke that sometimes the causal dual is just the same operad, the same letters read backwards, right? That was with Schnabl and Leibniz, and here we have H-Lie and IL. And then you get this. So you get a graded vector space, which has tensor products now of arbitrary degree, right? Before we had the binary products of arbitrary degree, binary operators of brackets of arbitrary degree. Now we have tensor products of arbitrary degree, and there is a differential that doesn't satisfy, that's not a derivation, so it doesn't satisfy the Leibniz rule on the nose, but it actually has an additional deformation in it, right? And it's this deformation that introduces the alternator and that allows us to have more freedom than in the case of L infinity algebras. Okay, so explicitly you can see a duality between H-Lie just by looking at the operations that you have on H-Lie, and on the IL algebras, they are really encoded in the differential, right? And then the condition q squared equals 0 corresponds precisely to the conditions that we had previously on the H-Lie algebra. So, right, so causal duality does our job. We constructed H-Lie, which generalizes Lie in a nice way, constructed the causal dual. And once we are there, of course, we can define EL infinity algebras in a straightforward way. So they are homotopy H-Lie algebras, and you just define them by general differential on a graded vector space. And then you get all these higher products, just what you know from L infinity algebras. So differential, binary pi product, cubic product, and so on. But all of these now have an additional label, I and ij, that run over the natural numbers, right? And you can have now, you have much more freedom in the products that you have, because there will be alternators, higher alternators, and so on. And these operations, I should mention, they're no longer graded antisymmetric, as in the case of L infinity algebras, but they violate this, and the violation is controlled by these higher alternators that you have around, right? So abstractly, it's very simple. Of course, if you want to work out the concrete cases, it gets a little bit more difficult, right? You have q squared equals 0, and you have some generalized version of homotopy Jacobi identities, and everything comes out in a straightforward manner. Okay, so of course, we recover L infinity algebra in a special case, namely, if you put all of these products 0, unless I is 0, ij is 0, and so on. If you do that, then you just fall down to L infinity algebras. So what are the nice properties of these? Well, first of all, they generalize DG Lie algebras, they generalize L infinity algebras, they generalize Reutenberg semi-strict, semi-strict Lie 2 algebras, and Deling's weak Lie 3 algebras. So everything that's known in the literature is being consistently generalized. They specialize Leibniz algebras and homotopy Leibniz algebras. And now there's a modified homotopy transfer on these. This is really what makes them to homotopy algebras. So what you heard in the previous talks about homotopy transfer, to transfer L infinity structures to other spaces. Here there's a modified homotopy transfer, which is actually quite interesting. It uses a modified tensor trick that you need to use. That allows you to map EL infinity structures to EL infinity structures. I mean, this is guaranteed to exist by abstract nonsense, but I mean, you have to work out the details how this actually works, and that's quite nice. So there are various theorems that you know from L infinity algebras that are satisfied. And the interesting thing is that whenever you have an EL infinity algebra, in each quasi-isomorphism class, so the right equivalence class to use on EL infinity algebras, you also have an L infinity algebra. So they're really generalizations, but whenever you have an EL infinity algebra, you can choose, if you're happy to work up to quasi-isomorphisms, to work with L infinity algebras. Now, of course, you can say, okay, what's that all good for? I mean, why should I really work with EL infinity algebras if I can choose to work with L infinity algebras? Well, in some situations, it's better to have the full algebraic picture. And one situation is, for example, the Courant algebroid. So how do these work? It's been known for quite a while that if you have a DG Lie algebra, as you have in Reutenberg's description of a Courant algebroid, then Getzler told you in 2009 how to get from this an L infinity algebra. Should say that this is a specialization of a previous result by Fiorenza and Manetti, right? This gives you then the Courant bracket on the Courant algebroid. What we did by putting Lie algebras in the middle, so we have a construction of going from the DG Lie algebra that the Courant algebroid gives you, you shift truncate in a very simple manner, you get Lie algebras, which are much, much easier than this translation actually. And then there is an antisymmetrization operation that gives you an L infinity algebra. So these Lie algebras are what are encoded in the Dorfman bracket. Before we only had the Courant bracket, now we also have the full algebraic structure of the Dorfman bracket. And it's then nice to have this concatenation and everything works out as you would expect. Okay, so let me switch this. Let me not go into too much of the details, I guess, because I'm out of time. Let me rather go to the good curvatures for the
5
non-Hillian.
minutes, actually.
Yeah. 5 minutes?
Yes.
Okay, so let me go to the good curvatures, actually. So if you try to generalize gauge theories to higher gauge theories to categorify, then what happens is the following. If you follow any of the prescriptions in the literature, essentially you end up with 2 gauge Lie algebras, right? In the strict case, you have a morphism from H to G and you have an action of G on H. That's usually called the cross module of Lie algebras in the literature. You get 2 gauge potentials, a 1-form gauge potential, 2-form gauge potential like this. And then you get the curvature forms, right? But as I already pointed out before, these are actually not the curvatures that you would like to have. There's many, many, many problems with this, which led to dismissing non-abelian gerbs by string theorists in particular and theoretical physicists. If you look at the BRST complex for this kinematical data, then it's not closed off shell. And there's then a condition that this fake curvature form, this here, the 2 form, needs to vanish. But then everything becomes locally abelian, and then you can ask yourself, why did I work with non-abelian gerbs if I can gauge everything always into an abelian form without losing any information, right? Also, there's a mathematical reason why this is not satisfactory, because you can't embed principal bundles into higher bundles if they have a connection. So this picture doesn't match mathematical or physical expectation. You can, as I said, correct this, and for this you need to add a particular term to a 3-form curvature, and this we called an adjustment in previous papers. You can't just do this in this case. I mean, in the literature you find this all over the place. That's in heterotic supergravity, that's in Urs Schreiber's and Hisham Sati's discussion, but you can do that in quite a few L-infinity algebras. In particular, there's a quasi-isomorphism class where you can do this consistently, and everything works out nicely then, right? So this is kind of the archetypal example that you have, namely the one that's important in heterotic supergravity. So the observation is it's not clear where the structure constants from adjustment come from, but there's a family of weakly 2 algebras, so 2-term EL infinity algebras that sit on top of this gauge L infinity algebra that you would use. And within this generalized family of EL infinity algebras that sit on top of the gauge L infinity algebra, you have precisely the adjustment as an algebraic structure, namely it's the alternator. Okay, so then you can ask, okay, is that a general feature? And indeed it is. The adjustment data come from alternators in weakly N algebras. Okay, so the theorem is then that any EL infinity algebras that can be adjusted from the Getzler construction or refinement of the Getzler construction naturally allows for an adjustment of the resulting curvatures, right? And we have, of course, the explicit formulas for all these, and there's just special cases. I should say that this adjustment discussion, or this whole algebraic discussion, had been attempted by many people, and there's quite a bit in the literature. But and they kind of worked towards the axioms in a manual way, right? So they knew what they wanted from gauge supergravity and from double field theory and from these situations. So they essentially guessed the axiom, and I'm impressed how close they actually got, right? So mathematics then tells you how to complete these axioms and how to get the full H-Lie algebras, right? Okay, then you can apply this to the tensor hierarchies that appear in 5-dimensional gauge supergravity. Here you see the curvatures. The blue part is what you would get if you did naively higher gauge theory, as in the non-abelian gerbs. And the red parts are the adjustments that you find if you use our technologies. And of course, these are precisely the adjustments that people found kind of manually by going through the construction, by having everything transform covariantly, right? I mean, from our perspective, in the supergravity literature that's derived at the level of the field theory, we show that this has an algebraic origin and that you can construct everything purely algebraically, and then you obtain this directly, and you don't have to work in any further sense, right? Okay, so the summary is that we constructed some generalizations of L infinity algebras. So there's in particular H-Lie algebras in this, and they have lots of applications in the tensor hierarchies, in double field theory, in everything that involves higher curvatures, essentially. And they have a homotopy version that are EL infinity algebras, which have a number of mathematical applications I couldn't talk about today. So the interesting thing is that the physical applications only required the H-Lie algebras. So I didn't really have to go to the homotopy version of EL infinity algebras. H-Lie, if you looked at all the applications that I gave, actually they were already sufficient, right? So you could ask, okay, is there a true non-application for really homotopy, the homotopy version, where you cannot work with just H-Lie algebra? So that's an interesting question that's left open. And yeah, so some of the above constructions beg to be lifted actually to the EL infinity case, and we haven't done this yet. Okay, sorry for rushing a little bit through, but I think I'm out of time now, so we should stop here. Thank you very much.
Thanks a lot for the seminar. You are perfectly on time. So it's time for some questions. Is there any? Okay, there is already one by Ivo, please.
Hi, Christian.
Hi, Ivo.
It's a very nice talk. Thank you.
Thank you.
So I have 3 questions, actually. I'll just list them. I think they're very short.
Okay.
The first one is, I somehow didn't grasp the operand that's underlying it. Did you display it?
No, I didn't display it. I just essentially described an algebra, and you have to work back what the operand is. So it's essentially, this is the algebra, right? So that's the H-Lie algebra. So you have to export these relations. It's a quadratic linear operand.
I see. Okay.
That's the interesting part of it. And this is how you get away. I mean, this relation here, you see where I'm at the moment, this has a quadratic part and there's a linear part is over here. And this is what brings in the alternator and makes everything interesting, more interesting than the, well, weaker than the L infinity case, I should say.
I see. Now, the second question is, it seems to me that what you've been doing would work just as well for the associative case. Is that correct?
Yes, absolutely. You could do that. Yeah, you could define weak A infinity algebras, absolutely.
Right.
The reason why we haven't really done this, because even for the true EL infinity algebras, we don't really have a good idea of the applications. As I said, these H-Lie algebras seem to be okay. They seem to be sufficient. So for all the applications that we are aware of, I mean, there are some pointers that show you that clearly beg to be generalized, right? But it's not clear, so this is why we haven't pushed it further. But absolutely, yes, you can do the very same thing.
And the last quick question, is there an involutive bialgebra version of this? Or is that not?
Yeah, we haven't looked at this. Of course, I mean, I would expect that you could lift this up, but I haven't looked at this at all, so sorry, I don't know this yet. That would be, of course, very interesting. I have no idea what this means in the context of, you know, field theories, where you would say BB corresponds to L infinity, or also in the case of string theory, string field theory, whether this has any meaning or whether you can use that for anything. I'm not sure.
All right.
Yeah.
Thank you very much.
Thanks.
Is there any other question? Okay, Yuji, please.
Okay, thank you for the nice talk. So you mentioned in the middle of the talk that the stratification theorem, right?
Mm-hmm, yeah.
So if I understand correctly, that means that physically you can make the theory cubic, right?
Yes, exactly.
Existence of the cubic thing.
Yes.
So, but then I've been always curious about this, because this seems to imply that we can have a cubic closed-string field theory. Could you explain a little bit more about this theorem?
Yes, I mean, it's a general feature of certain operands, right? That they can do this, right? I mean, if effectively what you do is you trade your you trade your higher brackets, the complication that you get in your higher brackets, for much larger spaces, right? So, for example, I can give you a very concrete example that probably may give you some feeling for how these things work. You see here, I looked at the stringly 2 algebra, right? So this is a 2-term L infinity algebra. It has Lie bracket here, and there's an additional mu3 that encodes 3 elements from here into there, and it's just the, you know, the Cartan killing form with its usual Lie algebra 3 cocycle, right? So with a Lie bracket inside, and now this cocycle, of course, you can you can transgress it, right? And if you transgress it, that means if you have a 3 form on a manifold, you can map it to a 2 form on loop space of the manifold, okay? So this 3 cocycle on this particular space, you can encode it as a 2 form on the loop space of G. And then what this 3 cocycle does for you, it just encodes a particular Kac-Moody extension of the loop group. And so I can work here instead with based paths and based loops. And then the 3 bracket will be encoded in a binary bracket. So what I did is all the complication that I have with having the 3 bracket and working with the true L infinity algebra as opposed to DG Lie algebra, I actually traded them for the benefit of working with the DG Lie algebra, but in a much larger space. So I have to enlarge my space, right? Yeah, that was probably a little bit too complicated. Another perspective is to just say, look, imagine that you have a field theory with quartic interactions. You know that you can blow up the quartic vertex and you can replace it with 2 cubic interactions if you introduce an auxiliary field in between, right? So that's probably a very simple example of a stratification, right? Imagine that you have phi to the 4 theory. The phi to the 4 vertex is encoded in mu3 in the cubic product of an L infinity algebra. You can imagine that in the vertex you introduce an auxiliary field so that you just have cubic vertices. You blow up the vertex. That's done in the context, for example, of the double copy. If you know happen to know that the double copy color kinematics duality, then they always want cubic vertices. And then you traded this, but at the price that you have more fields around, right? So you have these auxiliary fields around that you need to take care of, right? I hope
So do you have okay, so do you have in principle, you have a procedure to make the cubic closed-string field theory cubic?
Yes,
so
but the space will explode, right? You will go to iterate. I don't know even know if you can do that if you really want all the high products turned on. If you can truncate your L infinity algebra at a certain arity of product, you can certainly do that, because all of these products essentially encode co-cycles. And what you can do then is you can take iterated loop spaces, so loop space of the loop space of the loop space of the loop space and so on. And then you transgress all these co-cycles into binary forms on these iterated loop spaces. And then you can translate them into binary products. But you see, the space explodes, right? At first you have your space of string fields, and then you take the loop space on this of string fields, and then the loop space of the loop space and so on. So yes, in principle, you can do it, but you trade it for horrible, well, not horrible, but rather tame infinite dimensional spaces, but it's still the number of fields explodes, right? That's a problem.
Okay, thank you very much for the nice explanation. Thank you.
Okay, thanks a lot. Any other question? If not, we thanks Christian again for the talk, and now there is a break. I have just read on the chat that the last speaker cannot give her speech talk today, so let us the organizer decide what to do.
Yeah, so what we will do, we will have a longer break now, 15 minutes.
Okay.
Oh, it was the same break as before, I guess. 15 minutes, and instead of the talk, we just have the discussion section.
Fine, perfect.
Yeah.
The ghost numbers are of the I didn't record what the ghost numbers were of all the every time I was writing something is exact. But
yeah, I'm asking because so for example, the kinetic operator considered by Takahashi and Tanimoto has a nice. It's a very nice expression, and it doesn't. And the cohomology is vanishing at the ghost number 1 sector, but it has a non-trivial cohomology at an shifted ghost number sector. So, and but solution associated with this kinetic term is slightly singular in the written theory, but in the case of theory with stubs, I think we may have a more regular solution, and then we may have a more So I was wondering if we can use this kind of
their
kinetic
construction.
operator. Yeah.
Yeah, so I think the question of the cohomology there is a little bit strange. They also claim to construct a contracting homotopy, which trivializes the cohomology. So there's some question of what states should be allowed. I guess that is a little bit.
Yeah, there shouldn't be a homotopy operator that can apply for the all ghost sector. But if you only need a cohomology to vanish at the ghost number 1, there must be some operator, right?
I think they had one that applied to all ghost sectors, but all ghost numbers. But there was some ambiguity that arose when trying to use this operator in connection with their representatives of the cohomology. So whether that means the homotopy operator is singular or their cohomology is singular, I don't know. I think they would have to comment on that. The other thing is their solution is kind of based on this identity string field, and I'm not really sure that is very meaningful in the context of a homotopy associative algebra. So I'm not.
Yeah, that's why I'm asking.
Sure.
So in the case of written theory, it's singular, but if you can add stubs, I thought they might be make it a little bit more regular. So that's why that's why I'm asking.
Yeah, so I don't know what, I guess in principle, one can try to map this solution with the field redefinition, but it's not going to be an identity-like solution anymore.
It doesn't have to be
So-
identity-like. It should be better to have a less identity-like solution, right?
Yes,
That's
but then
why,
one can
yeah.
also ask why not do this with Schnabel's solution or
Yeah. So if you have a compact expression for the Schnabel gauge solution, or something that corresponds to Schnabel solution in the Stubbs case, I think it's fine. But if you have many terms with sliver term and so on, that makes the explicit calculation difficult. So that's why I was just.
Oh yes,
I thought that
So I guess you're thinking that somehow these wedge-based solutions really kind of are adapted for a particular conformal frame, which might not be suitable for if you add stubs, and maybe their solution would be better in that sense.
in some sense, in some sense,
Yes.
Yeah.
Yeah. So then one, in that context, maybe one can try to understand which, what conclusion wins out as far as whether there's cohomology or not. But I'm a strong believer in purely vanishing cohomology because it's the nicest result, and it's the somehow the result that is really strictly holds in the regular solutions that we know for the tachyon vacuum. So regular analytic solutions. So that's what I'm hoping.
Yeah, but your construction doesn't seem to. Okay, so your solution construction doesn't seem to require physical, solution to be physical or anything. So just mathematically, you have some solution which are vanishing cohomology, and you can use it to generate a physical solution that's interpret between different boundary conditions.
Yes.
Right.
So this is.
So tachyon vacuum seems to be that doesn't seem to be, it's an auxiliary role, right? Tachyon vacuum. So that's why I was thinking about kinetic operator, Takahashi Tanimoto kinetic operator, which might be also used. Yeah.
Yes. So
I just
yes. Okay.
Thank you.
Yeah, thanks for the question.
Okay, thanks. I have a question for Alex Arvanitakis. You show that the BPZ of the states with winding have some may have some minus sign. The question is whether this implies that the kinetic term has the wrong sign.
So are you worried about issues of stability and the like?
Just to understand, yes, more or less. This is the first question I came through. I couldn't ask, but now I can ask.
Well, we didn't look at the implication of the kinetic term explicitly, so I couldn't tell you what happens. It sounds like Dimitris did, of course, but on some level, you have the inner product, and it's sort of implicitly via the inversion map and so on. And you can work at it all day long. And it's really when we actually try to calculate it that we ran into problems. So I don't think, there he is. So I don't have much more insight with regard to what happens in the kinetic term.
Thanks a lot, in any case.
Yeah, so maybe I can just make one comment on that, one additional comment. Yeah, so this minus sign is basically required to ensure, I mean, one way of looking at it is to notice that it's required to ensure that the states have positive norm. So the kinetic term is just a normal kinetic term. It has positive norm, it's nothing strange. The states, by the way, these minus signs are not present in the expressions for the states, as far as I understand. It's just as Alex said, basically, that if you actually want to write things down in terms of vertex operators and you think about the maps, then you pick up these additional minus signs if there is non-trivial winding and momentum modes in the compact directions. But yeah, so all states have positive norm. They're physical. It's just the normal states that can propagate on a toroidal background. There's nothing strange about them. At least that's my understanding.
Actually, do they have positive energy as well? Because it could, in principle, come up in the quadratic term and the kinetic term, as Igor pointed out.
Yeah, so I think you can get things like the Higgs effect. Is this? So the mass spectrum is just the usual mass spectrum, right? Of the state with winding and momentum. So that contributes positive energy, right?
No, the mass spectrum is fine. That's determined by the BRST differential. That is fixed. But the question is, you evaluate C cube C for some state C, and the contraction is with the BPZ. And the concern that was raised, I think, is the minus sign that enters just through the inner product enough to flip the sign of the kinetic term? Which we didn't investigate this, actually. Maybe we should have. But I was wondering whether you did.
But Dimitris is saying that the norm is positive, right? These states have positive norm. And if they have positive norm, I would think that the kinetic term will be positive. That there is no problem because QB has positive eigenvalues. Right? It's C0, L0.
Ah, that makes sense. Okay. But they're positive with the correction is the point, right?
Yeah, I think that's what he said, if I understood.
Yes, exactly.
Yes.
Because one thing is that you use the Hermitian conjugate. In this case, I don't have issues. But if you define the kinetic term as it is usual in Stringfield theory with a BPZ, there is no Hermitian conjugate inside. So this is my issue.
Yeah, good. Very good question. So the thing is that of course, the Hermitian conjugation is what one really needs in Lagrangian signature, right? But if you're doing calculations in Euclidean signature, you need the analog of that. And the analog of that is Euclidean, taking the Euclidean adjoint, Euclidean conjugation. At least this is one way of doing the computations. Yeah, so this is actually identical to what you would obtain if you did Hermitian conjugation in Lagrangian signature. You can actually derive it from that. That's why this notion of Euclidean adjoint is convenient, because it has this correspondence with the Hermitian conjugation. But I know that in string field theory, you use BPZ, and of course I'm not an expert in string field theory, so I don't really understand how everything is. I mean, yeah, there are many gaps in my knowledge to make all of the links precise in my head.
I think the extra sign would, in principle, change the reality condition on the string field. So you get it from relating the BPZ one, that is complex linear, to the Hermitian adjoint, which is antilinear. So if you have an extra minus sign, then what you think was real is actually imaginary, and vice versa. Maybe somebody else can
Yeah, so the point that in string field theory, you indeed want to have your BPZ conjugate proportional to the Euclidean adjunct up to some sign, which is one way to phrase a reality condition, like, so for example, which Barton had in his old paper on the bosonic string. But then Ashoke had a paper, so I think he might comment more. But so this is one way to phrase a reality condition, but you have a bit more freedom. And maybe with this freedom, you can reabsorb this sign. So maybe Ashoke can say more about like how it would connect with your paper on this.
Yeah, I think it's basically a generalization of what Barton did for bosonic string theory. You have to assign reality to each string field, right? And you have to make sure that, so you first assign the reality to physical fields so that the physical fields are positive kinetic operators. Okay, so that fixes whether the field is real or imaginary. Okay? Then you start assigning reality condition to the auxiliary fields, okay, which do not directly get constrained, but they get constrained by the cubic interaction because you want the cubic terms to be real, right? Once you declare which fields are real, then the whole action should be real. And that's how you fix the reality condition on all the fields, right? But the reality condition on the physical fields is essentially by requiring that the kinetic term is positive. So you define the inner product using BPZ, right? Because that, the various identities are easier to implement if you use the BPZ inner product. But then you use the freedom of declaring which field is real and which field is imaginary.
So in conclusion, some fields must be taken imaginary and some real, depending on the winding, whether n times w is equal, is odd or even. And then you assign the reality onto auxiliary field, just requiring that the whole action, at least the cubic action, is real.
Yeah, that's the procedure one follows, exactly.
Okay.
But it's a non-trivial thing to check that the whole action becomes real, that there is a consistent assignment that gives the correct sign kinetic term for the physical fields, and at the same time that makes the whole action real.
Clear. Okay.
That's the consistency condition you should check.
Yeah, yes. If you believe that it is consistent, the theory is consistent, it should work. Let us say this way.
Yeah, the point is at the level of testing gauge invariance, it doesn't matter. You don't need to know which is real and which is imaginary. It's only when you try to, say, look for classical solutions, then you need to declare what is real, what is imaginary.
Okay.
Right? Because some solution, you may think that you have a physical solution, but it may turn out to be a complex solution, right? Which is not physical. Yeah, maybe Barton can add something. I mean, I can see.
Well, let us say this way. It could be that complex solution can be understood as instantonic solutions. Let us say this way. It's not clear that they have no meaning, at least to me.
Yeah, but I'm thinking of more as solutions which are supposed to be objects in the theory, right? Some solitons, for example. So those should be real solutions. Once you declare the reality condition,
yes,
then only real solutions are allowed, right?
Yeah, if you wanted to interpret as real things, they must be real. But, well, sometimes complex solution can be understood as instantonic solution. So I don't know.
Yeah. If you want instantonic solutions, yes, I agree. But that's a different class of solutions.
Yes. Okay.
Yeah. I think Barton wants to say something.
No, I think you summarized it very well. Nothing to add. No.
Any other questions? Okay, we have a question from an unknown person, Yuji.
Sorry, but at this time I want to ask a question to Alison. about the gauge invariant wave calculation. So I've heard that the Maldacena did a very complicated calculation for the cosmological 3-point functions for the model for the inflation. So I'm not familiar with that, but I'm wondering if your way of gauge invariant wave calculation helps his calculation simpler, or is it?
Thank you for the question. So, well, we haven't okay, so we haven't computed any correlation functions. So I don't know if that part becomes simpler, but I mean, indeed, because we don't, so what Maldacena does is that he does the computation like twice to make sure that his gauge is fine. And so in our method, we wouldn't have to do that because we just have gauge invariant variables. So in principle, I think it would simplify computation.
Yeah, I've heard that Maldacena did a calculation for several gauges to check that the correction and the result is correct. And if you can do it in a simpler way, even this can be impressive, right? So then, so that's why.
Yes, I believe so.
But I think it's very interesting. Yeah, thank you for the very nice talk.
Thank you.
Other questions? I have still a question for Alison Pinto about the simple example, or almost the simplest example. When you consider, instead of U1, you consider X U1, that is a theory with a scalar, a U1 with a scalar, with a potential which breaks between quote unquote, because it doesn't break actually nothing, but symmetry. So in this gauge, in this theory, it is somewhat natural to choose as gauge fixing the unitary gauge. So what happens when you choose the unitary gauge instead of a covariant gauge? Because it would seem that all what we have done changes quite a lot. So have you thought about this or not?
I haven't thought about that specific case. But I mean, so yeah. But so in our procedure, you don't have to pick a gauge. I mean, yes, it's equivalent to picking a gauge, but you don't have to pick a gauge. You just construct gauge invariant variables. So we don't have to think about, and we know how to construct them because we have this procedure. So the gauge or the gauge invariant variables that we chose are the right ones, and we don't have to worry about what other choices we could potentially make, for instance. I mean, yeah.
So, okay, let's formulate it this way. There are many gauges, not all of them are as good. So, and the question is, okay, you can think of writing many different gauge invariant variables, but sometimes it is reasonable that you cannot cover the whole space with only one set of gauge invariant variables.
Okay.
So,
sorry, may I add some clarifying remarks?
Yes, thanks a lot.
I don't know, attempt to be clarifying. So as Alison was emphasizing, indeed, we're not conceptually, we're not picking a gauge. We are rewriting, we're reorganizing the fields in terms of gauge invariant variables. Now, operationally, that is, it is the same as gauge fixing. So, for instance, the Maxwell example is like picking Coulomb gauge operationally. But you may always go to a different gauge choice at the end of the day, because you know how the gauge invariant variable is expressed in terms of the original fields, and so you may always re-express. So in principle, you can go to any other gauge. Now, if there is, of course, an assumption to define these variables, which may not always be valid, which is in the case Alison was discussing, that the spatial Laplacian is invertible, that you need to do the sort of Helmholtz decomposition of a vector into a divergence-free vector plus the gradient of a scalar. So if that is not true, then you can't do that. And so that's a potential obstruction, but it's sort of whatever you do, it's at the heart of cosmological perturbation theory, that you can always do this decomposition, scalar vector tensor decomposition. So that was the cosmological case, is really the motivation. So it's not necessarily useful for Yang-Mills theory as such. I don't know, maybe it is, but not necessarily. And there was something else I meant to say. No, I forgot. But I don't know if does it address some of your concerns?
Yes,
or
yes, it's clear. But I can explain in more detail why I was talking about covering the space. I don't know whether you are more or less familiar with the Hilbert duality NC equal to NF is using let's say an algebraic geometry description of a moduli space. Okay, the algebraic moduli description of a moduli space, it is obviously gauge invariant, but it cannot be covered by using only some. It is multiple-paged. You have more variable. You need more to cover all the whole space. You need more variables and some relations among them.
I see.
So the question is the covering. It's clear that you can define a gauge invariant operator, and this is perfect. But it is not clear to me in which. Whether there are obstruction to cover the whole space of a configuration with a set of gauge invariant operators.
But
it's completely clear that for your purpose, it's perfectly fine. It was just a curiosity.
Right. But is the issue that there's not a globally defined one form, let's say, in this context?
No, it was using some scalar, well, yes, it's more or less a scalar gauge invariant bilinear, multilinear in the gauge fields, but okay. But
okay. Yeah, but I mean, what we are doing is strictly in the realm of perturbation theory, I would say. So
okay.
So there, at least, yeah. That's what, I think there was someone raised the hand.
Just a brief comment on that. So I think there's this statement. I mean, it would be good if an expert in the audience can clarify. But I think there's a statement that algebraic gauge gives rise to a local effective theory, whereas a differential gauge gives rise to a non-local effective theory. Or, I mean, in the present context, to be more precise, the vector potential in unitary gauge can be obtained from a local gauge invariant operator, whereas if you write the vector potential in, for example, Lorentz gauge, then that can only be written in a gauge invariant way as non-locally. So there's this curiosity about the distinction between differential and algebraic gauges, but I'm not an expert, so I mean, it'd be good if somebody in the audience can elaborate further.
Well, so quick comment is that the action is non-local in terms of gauge invariant variables. because but it's non-local in space because of the invertibility of that they need the inverse Laplacian. So
Actually, I'm sort of quoting a paper by Polchinski where back in 1987, where he basically reached this conclusion. I don't know.
it sounds plausible, yes.
His vertex operator papers, where he discusses about all these different gauge choices in principle and in general in any field theory, and which ones give rise to local effective actions to non-local and so on. Like static gauge, for example, gives rise to local effective action for number-Goto action. Whereas
but the meaning of effective action in his context is what? What's the effective here? Integrating out something else, or it's not just going to a particular gauge?
If you want to write the vector potential in unitary gauge, that it can be obtained from a local gauge invariant operator, whereas if you did the corresponding thing in Lorentz gauge, it could only be written in a gauge invariant way non-locally.
I see.
Perfect. Any other questions? We have had a lot of talks, so please.
There's a question.
Yeah, there is a question, Nico.
Yes. Okay.
Hello.
Sanjana. I hope I have pronounced the name right. I'm not sure. Sorry. Please.
Yeah, that is right. So I just wanted to say that I mean, I find this whole idea that I mean, you could get gauge invariant variables you know, through something through an algebraic way, like the homotopy thing. It's a completely new thing, and I think it's really cool. And I guess I missed out on like which part of it specifies the gauge group in the chain thing. You guys might have mentioned it multiple times, but then can you just kind of go over that once again?
So you mean which what do you mean, which part specifies the gauge group?
Like you are generating gauge invariant variables from non-gauge invariant ones through some homotopy method. Like, oh, you know, I didn't get all the details of that, but like which like when you say gauge invariant, it's gauge invariant under a particular gauge group, right? Like, and under the action of like a particular gauge group. So where is the information of that gauge group in this method? Like, I kind of couldn't catch that if you had already mentioned it.
No, yeah. In fact, I think I didn't mention it because that's. I mean, you start with an action that has a gauge symmetry already, so that's sort of your starting point. And then you encode this free theory with in a chain complex, and those differentials in the chain complex are dictated by the gauge symmetry. and your interaction.
Like when you say, okay, like when you say gauge symmetry, it does mean that there is a particular symmetry group, right? Like, so, like which group do you start with, or like where do you like where is the specification of that group in the entire description? Because when you say gauge symmetry, or like the theory is invariant under these gauge transformations, then I mean, like you just specify, like for example, say SUN. So in this particular method, or the description, like if I want to describe SUN gauge theory, you know, like where do I see that in this description?
In the homotopy transfer.
Yeah.
Well, I think she's asking if you specify specific Lie algebra that you want to have. Let's say let's do Young-Mills theory, and you're asking where, and I specify the structure constants for SUN. Let's say. I think you're asking where in this big story, where does it show up? And the answer is in the brackets of the L-infinity algebra. So that's something that goes beyond the chain complex, which just sees the linearized transformation. So there doesn't make a difference what the gauge algebra actually, the structure constants actually are, because it's just the number of parameters that you see. So in order to see the group, the actual group, you have to go beyond that. And that means you have to look at the actual L-infinity brackets, which then by the homotopy transfer are moved to another space if it exists. Is that, was that did this address the question?
Kind of.
So in other words, if you want SUN, you have an L-infinity 2 bracket on the space of gauge parameters given by the structure constants of SUN. Or if you pick another gauge group, that you would change that bracket. And then, of course, if you do homotopy transfer, that will propagate to the other space.
Okay. Oh, okay.
There is a question.
Bhattacharya?
Thank you. Yeah, it's related to what was asked earlier. So I think the X1 vector space contains the gauge field, so that will have the information about the gauge group also, right? Like X0 contains the field, X-1 is the equation of motion. So X0 contains the gauge field. Shouldn't there be also the information of the gauge group? Say you have U1 in the gauge group, you have only like this U1 translation. That is what I thought. No, I was mistaken.
I mean, you have gauge fields, but like those gauge fields transform under certain gauge transformations, right? So
yeah, so
like,
those are in X1, right?
Acha. Okay, like yeah, it might have been discussed, but I kind of missed on that. Like, okay.
I'm also not sure. Means experts like I thought that maybe I was mistaken.
Okay.
I think gauge group
also
is
had
not
another.
Is not really physical. It may depend on how you describe the theory.
Yeah, of course. Yeah, gauge group.
It's true that the gauge group is not physical. You had another question?
Actions and particles, or whatever, you know, fields and excitation. And like, I also have another question. this thing is like, so I've heard from a couple of other seminars that gravity does not have U1 symmetry. Can this this description, which is a homology description, be used to conclude something like that? You know, I don't know how that was concluded earlier, but you know, can we?
I don't think so. I mean, there's not clear what the context was. I mean, are you referring to things like that are no global symmetries in quantum gravity?
Yes, yes.
I mean, that is the arguments for that kind of thing are very different and have nothing to do, as far as I can tell, with L-infinity algebras. Which in any case, the natural playground for L-infinity algebras are gauge symmetries and not global symmetries. So
I think I came across some statement like
here's a bad connection.
I think we lost the
can
connection.
see.
Yeah.
I think vision has come, but yeah. So, like, can we use homotopy and like this description to figure out what kind of gauge symmetries do some particular fields, you know, like gauge invariant field or whatever, have, or like some particular theory should have, etc. Like,
I don't think so. I mean, you have to. I mean, the point is that L-infinity algebras are extremely general framework for any kind of gauge. If it's sort of healthy, any kind of gauge theory fits into that framework. So that turning this around means that it won't tell you what is the correct gauge group in nature, which anyhow is not a meaningful statement, because gauge symmetries are not physical. So you may have two descriptions of the same physics with different gauge groups, and but both descriptions would have the claim is both descriptions would have an L-infinity formulation.
okay.
And then the interesting question is there a natural formulation to go from one to the other in terms of the algebras?
Yeah.
But as the framework is such that it won't tell you, I think, what is sort of quote unquote the correct gauge group.
Okay. But yeah, I think this idea is really cool.
Yeah, thank you.
Okay, we can move on and see whether there are other questions.
Can I ask another question?
Yes.
Hello?
It is not only on the same subject. Yes, of course.
Okay. Yeah. I'm sorry. I might be asking a lot of naive. Etc. So,
No, sorry.
So Jana, we're losing your audio.
Yes.
I think it's okay to ask naive questions, but for example, if you want follow up, you can start using the Zulip chat, and then there a broader audience would have access to it and have more let's say a more adequate space to elaborate on the answers. Is that okay?
Yeah. Yeah,
that's fine.
yeah.
So the Zulip chat will be maintained for as long as the community goes on. And it will be open to all. So I think we might have a better chance to answer these things there.
Okay.
And we can write the questions.
Yeah.
So, other questions? I have just a curiosity about the talk by Christian Saemann about the extra terms which are added, because as far as I understand, if you use a straightforward prescription, you miss some terms in the higher gauge curvature. So the question which I not complete, well, I followed the philosophy, but not the details, just to be sure. But what I'm not sure about is whether the terms you add are unique or you have some freedom of it.
Yeah, that's a good question. I mean, you do have freedom. So first of all, if you don't add these terms, you run into all kinds of problems because you need essentially all but the top curvature forms to be 0, and that excludes a lot of interesting cases. You can do a higher Chern-Simons theory in this way, but you can't do anything else. You do have a little bit of freedom there, but essentially the cases that I've studied so far, they're all equivalent essentially. It doesn't matter which term you choose. It then modifies your gauge transformations a little bit, right? And then, but you can show that the gauge orbits are still equivalent, and you can map gauge transformations onto each other. Yes.
So it is as if the theory is more or less unique.
Yes, exactly. Right. I mean, it's not the theory, right? It's the kinematical data. That
okay,
the dynamics then you have to put on top of this. Yeah, absolutely.
Yes,
right. So for example, I mean, in string theory, we know a lot of the Bianchi identities that we want, like DH is FHF and things like this. And that fixes a lot of the adjustment. That fixes essentially the adjustment for you, right? So in most cases that we would be interested in, the adjustments pretty unique, right? And if you use the construction of generalized tangent bundles as GDG manifolds, then also you kind of find unique adjustments essentially, or well straightforward versions certainly of adjustments. I think all the other adjustments are essentially boiled down to field redefinitions essentially. Yeah.
Okay, just a curiosity. What are, since we are talking about string theory, and I'm thinking to the talk by Sen about the magnetic and dual field strength.
Mm-hmm.
Can you say anything about this?
Yes, you mean the very nice action principle to recover to recover self-dual forms and things like this, or
not only the self-dual, because self-dual is F5, but when you have there's a talk about type 2B, you have F3,
right.
F and F7, so they should more or less coexist if you use this democratic principle. So can you do anything in that direction in a straightforward way, or you have to tweak a little?
Unfortunately not, right? I mean, that would be very nice. Well, what I can say is that if you the action principle that Ashoke gave is very, very natural from the perspective of the L-infinity algebra. So that's for a different perspective on this, right? If you write down the L-infinity algebra that you've seen in the previous talks for a self-dual form field, right? Just the L-infinity algebra without extending it cyclically to the action. Then you can make it cyclic by just considering the cotangent bundle. Okay, and then you have a straightforward action principle. And then if you rotate your fields a little bit, then you get straightforwardly this the action that's in Ashoke Sen's paper. Well, what's nice about this prescription in L-infinity algebras is that you immediately see that the new forms that you have and the new degrees of freedom that are encoded there by minimal model construction, that they are just gauge trivial. You can just gauge them away. You can introduce new gauge symmetries, and then they're just removed. So that makes the discussion a little bit simpler, perhaps. But yeah, unfortunately for the electromagnetic duality there, I don't have anything straightforward to say.
Okay, thanks.
Yeah.
Other questions?
I mean, if there's no question, can I ask a naive question actually? Because there's so many experts around, in particular, probably for Evo. So what's the current state of the art? Imagine that I want to describe open-close duality in a homotopy algebraic framework. So I would like to have a homotopy algebra in which I have both open and closed. Which homotopy algebra would I use, right? Would I use some combination of IBL infinity and IBA infinity, or what is kind of the state of the art there?
So the open-closed homotopy algebra is really a morphism from the it depends if you do quantum or classically. If you do it classically, then it's kind of an old story, which goes back to Stashev and Kachura.
Mm-hmm.
So it's a morphism from the L-infinity algebra of the closed string to the co-derivations on the vector space of the open string.
Right. Mm-hmm.
So that's the story there. If you do quantum, then it's an IBL infinity morphism. So the open-closed homotopy algebra, open-closed homotopy algebra is really an IBL morphism from the L-infinity algebra, the IBL infinity algebra of the quantum closed string to the co-derivations with the Gerstenhaber bracket.
Mm-hmm.
And the co-derivations of the open string.
Oh, okay, very good.
There's also an operatic form of it, but I think for this, because it's IBL, you need the properats rather than
sure.
Mm-hmm. So I think that's
okay. Perfect. That's very helpful already. Thank you very much. Yeah. And I guess I look it up in some of your papers and find
this. Yeah, actually quite a while ago with Corbinian Münster. I think it's a CMP, maybe 2014. Sorry, 14 probably.
Okay, perfect. Thank you very much.
2014 or 13.
Mm-hmm. We'll find it. Thanks.
You're welcome.
I have a follow-up question to Ivo.
Yeah.
Hi.
Hi.
Yeah. So I would like to ask. So, is there a consistent open-closed string field theory which would correspond to the classical open-closed homotopy algebra of Kasia and Stashev?
Oh, it's just. I mean, there's really nothing. Oh, yeah. It's really, in a way, it's nothing new. It's just an algebraic formulation of Zwiebach's open-closed string.
Because I thought that once we start considering open-closed string field theory, we have to be quantum automatically. So, but there is this classical open-closed homotopy algebra.
That's right. It's not consistent. To make it consistent, you have to do the quantum version of it, and that's the IBL. That's the IBL infinity version of that. So,
I see.
And so the open-closed homotopy algebra, as we just said, is this IBL morphism from the IBL infinity of the closed string to the co-derivations on the open string, and it's realized just by Zwiebach's open-closed string field theory. So the realization, I mean, in a way, sort of backwards. The field theory was there, and then we just formulated it in an algebraic way.
Okay, thank you.
it has some uses, and you can use it to discuss some aspects of background independence and things like that, but there's no new theory.
I think maybe we could finish. If there are no more questions. We would like to thank all the lecturers, panelists, and speakers for this nice conference, and of course all of you in the audience that had so many good questions, so many interesting discussions. We hope to see you all again next year, I guess, but we don't know yet who is going to organize it or where. Hopefully it will be in person. But I think that's it. Thank you all.
Thank you.
Maybe this is a good opportunity to also thank the organizers. They did an excellent job. And let's hope that this continues. I think, I guess the journal club will continue, right?
The journal club will continue. We will try to make it very regular, systematic, and nice, so everybody can attend it and learn.
Okay. So we'll send an email.
Organizers
So we'll send an email with a link to register to the mailing list so that we're sure everyone has it, and then we'll send information shortly after. And just to be clear, so check also your spam, because we had some problem with spam with this mailing list. So if you don't get emails from us, but you see that the journal club is announced on the website, just check the spam or just write to us, but to be sure. And then when we know it works, then it will be simpler, but yes. So we
and checking the Zulip regularly, I think, is a good idea, because we will definitely post everything on Zulip, and we will make use of the Zulip in a very regular fashion. So checking it is a very good idea.
Okay.
Okay, thank you.
So have you all a nice weekend and nice dinner, lunch, or whatever you're going to have now.
Thanks a lot.
Okay.
Thanks a lot.
Bye bye.
Thank you so much. Bye.
Bye bye. Thanks a lot.